rule for BCR, whatever. So there's no risk of credentials leaking to the wrong place. And even if credentials get leaked, they're only going to affect one resource. So rotating credentials is simple with Renovate. Update something involved, and external secrets pick it up and syncs automatically. So another problem is custom versioning for monorepos. So here is a real-world example of Renovate's flexibility. In our shared workflows monorepo, which is open source, shared Dash workflows in our Grafana organization, each reusable GitHub action is released independently using Google's release please. Tags look like this, like action name v123, rather than plain Semver. Out of the box, Renovate doesn't understand this format and either misses updates entirely or creates useless PR descriptions. The fix is Renovate's regex versioning. So we define a pattern that splits the tag into two parts, the action name, which is the compatibility prefix, and the actual Semver version. This lets Renovate correctly detect new versions per action. So beyond just parsing versions, we also use this to customize the branch prefix per action, which is really important, and craft meaningful commit messages, which is also important because our commit messages double as PR titles. So when your release strategy doesn't fit the standard mold, Renovate's regex versioning bends to fit your workflow rather than forcing you to change your workflow to fit the tool. And then as your Renovate configuration grows more sophisticated, it's easy to introduce errors like a typo in a regex pattern or an invalid option or a logical mistake. These errors can break dependency updates across your repositories, and you might not notice until updates stop appearing. To prevent this, we validate all Renovate configuration changes before they're merged. We have created a reusable validation action that runs the official Renovate config validator tool. It checks for syntax errors, invalid options, and logical issues in your configuration. So this runs automatically in our CI pipeline on every pull request. You can opt in or opt out of it if you want to at the moment. If someone submits a change with a broken config, they get immediate feedback about what's wrong and where to fix it before it ever affects production. It's a simple safety net that becomes increasingly valuable as more teams adopt Renovate and configuration complexity grows. So catching errors early means fewer broken deployments and faster development cycles. So in the slide, you can see a small flow chart, which what it does, what it means is that basically in that action, Renovate updates itself. So there is one action that runs this Renovate check with like a pinned Renovate version. So Renovate updates itself, and then once this action gets released using release please or whatever else you use, then Renovate runs again to update this action in every consuming repository. So as you can see here, I hope this is clear. As you can see here, the first PR is created by Renovate to update itself. Then once the GitHub action gets released, you get this really pretty PR with all the changes, the change log, and everything created by Renovate. And this is the actual change that Renovate makes in a single repo. So it updates the hash, and it also updates the semantic version by also keeping the action prefix. And with this, I'm handing over to Phil.
Morning. Can you hear me okay? Yep. Okay, so morning all. I'm going to run you through a bit more information on how we've set up Renovate and how we're deploying it in our infrastructure. What we've done to optimize running this at scale for the 1,400 plus repositories we support at Grafana Labs. Here's the overall view of our setup as it stands today. We're running Renovate across multiple cron jobs. Each one processes a batch of repositories in parallel. We chose cron jobs because they run at a predictable cadence, which gives us control over when and how repositories are processed. They're also isolated. When you're processing hundreds of repos, something will eventually go wrong in one of them. And with batch cron jobs, that failure stays contained while the rest keep running. One limitation of running Renovate on a schedule, though, is responsiveness. We've opted for 3 hourly runs, which give engineers several updates throughout the day while keeping the benefits we get of consistent load, predictable behavior, and the ability to treat each batch independently. Each cron job inherits the global configuration that Dimitri's just mentioned, so security policies are consistent across all of them, regardless of which batch a repository ends up in. We also use Redis to cache across all jobs. We're caching repository metadata, private package information, and shared presets, which means each job isn't refetching the same data from scratch on every run. At SCaLE, this is added up. Naturally, we've run into a few issues running this at the scale we've needed to. The first was rate limits. Early on, jobs quietly stopped raising PRs, and it wasn't obvious. There were no obvious errors, just silence. And it took us a minute to understand why. Renovate makes multiple API calls per repository, and when you're running hundreds in parallel, we were hitting GitHub's rate limits faster than we'd expected. The second was more subtle. GitHub app tokens have a 1 hour time to live. If a batch takes longer than an hour to process, the token expires mid-run, and any remaining repositories start failing with 401s. This is where our batch sizing has really mattered. We tune batches specifically so jobs complete within this window. Jobs can retry and failure, but of course the goal is to avoid that situation altogether. This is essentially, this token limitation is the main trade-off of the cron job approach that we've found so far, and the hardest ceiling we've had to work with it. Because we can't dynamically update config maps for batch runs already in progress, the token can't be refreshed mid-run. So batch sizing addresses both constraints, keeping jobs short enough to stay within the token window, and limiting how many API calls are in flight at once. The shared Redis cache reinforces the rate limit side further by caching package metadata and registry responses across batches. We avoid each cron job independently hammering the same APIs. Together, we've found this to be a reliable combination for staying within both constraints. Okay, so we mentioned that we get auto-discovery with Renovate out of the box. For our environment, we use this, and we use the filter feature that it offers to divide which repositories each batch processes expressed as regex. On first iteration, we maintained a manual list of repositories, which allowed us to roll out in stages and control the scale and cost as we gradually onboarded the whole organization. Over time, this has given us a feel for the right batch sizes that we mentioned, specifically keeping jobs within this GitHub app token time to live. Processing repositories alphabetically has given us a consistent way to divide the org into evenly sized batches, with each cron job handling a predictable subset. Any repositories we want to exclude are added as negative patterns and applied across all batches automatically. And the batching approach means that, again, load is predictable and it's easily tunable. If we scale out, we can add batches. If a particular batch is causing problems, we can isolate it without affecting any other repository runs. And the practical effect of using auto-discovery in this way is that we get the same control and predictability from a manual list without the toil. Okay, so to mention a service that we've built to help us alongside this. We've put together a webhook listener. A main advantage of self-hosting is that you own the infrastructure and you can extend it. And as mentioned, a main trade-off is how responsive it is, and in particular to when users are waiting for their own user-made requests to return. Mend.io offer on the hosted version supports on-demand rebase. You tick a checkbox on a Renovate PR and it happens immediately. With scheduled runs, that still functions, but the request sits there until the next cycle, till Renovate then processes that repository, and that can happen potentially hours later. So we built a Go service that listens for GitHub pull requests. When it detects the Repos box checkbox is checked on a Renovate PR, it validates the request and immediately triggers the Renovate run for that specific repo. Before launching, the listener fetches the GitHub app token directly from a Kubernetes secret, ensuring that each repository run starts with a fresh token. This sidesteps the time to live issue that I just mentioned. Rather than a token baked in at pod creation that could expire mid-run, every rebase triggered run gets one that's current. And the listener runs alongside a Dagger engine sidecar in the same pod. So Dagger spawns Renovate as Docker and Docker, as Docker and Docker container, which completes a default Renovate run. We're essentially handing over all of the GitHub history state to Renovate to manage itself, any branch state, PR state, and it can track and work in combination with how we run it in cron jobs. And we don't have to worry about any merge conflicts that we would get from potentially firing custom requests to GitHub. So we also handle queuing internally. If new rebase requests arrive while a run is in progress, they're held and processed immediately after. No external coordination needed. We consider two main alternatives to this: shelling out to Docker run or spawning a Kubernetes job per webhook, but both on review added overhead and fragility that we didn't want. A long-lived service means that we pull the Renovate image less frequently. Using Dagger means we can benefit from the layer caching that Dagger offers, and we have a single place to extend when we need new behavior, which leads us to where this is going. What started as a rebase trigger is becoming more of a general utility service now, a single place to add automation rather than building one-off triggers for each new need. And in terms of the other features, the last one that we've added is auto merge. So it's a feature that people are often are instinctively cautious about. The risk isn't the feature itself; it's merging things that you don't fully understand. Our approach is to replace that instinct with explicit auditable signals where possible, and we use a two-stage model for this. The first stage is an auto-approve bot. It runs two sets of checks. PR integrity, was this created by Renovate? Are all commits signed? Is every commit from Renovate? And package trust. Is this on our allow list? Is it a patch level update? Has the version been published long enough to avoid early supply chain issues? Any failure in either set sends PR back to manual review. And our webhook listener feeds directly into this. Because we have a service that already receives PR events, we can run more sophisticated checks there, like log validation and file history analysis, without needing separate infrastructure. The merge decision itself is handled as a CI check, so it slots into the existing PR workflow. By the time a PR reaches merge, enough signals have been collected that the decision is just mechanical rather than a judgment call. Okay, so the last part of this section, just going to talk a little bit about how observability looks when we're self-hosting Renovate and how it might look to you. One tool we wanted to mention that got us up and running fast is the Grafana Infinity data source. It lets you query the GitHub API directly from Grafana without building or maintaining a custom exporter. You'll see more of this in a demo in a second, but there's a couple of panels that are worth calling out now. On the right here, you can see 32. This is the security PR count. That's a live view of how many PRs are open across the org to fix security vulnerabilities. And we have two merge time metrics that we track. We have the top is regular dependency updates, and the bottom is security vulnerability updates and the time to merge. Over the course of the rollout, we've been able to measure adoption and response times using these, and we've actually seen them drop from days to hours, so we can see the adoption quite nicely. Together, these go beyond monitoring whether Renovate is running. They show whether it's actually having an impact on how our organization is managing our dependencies. And it's worth mentioning also that Infinity data source has been great for iteration speed, but our next step is to, as we've matured, to move this to a Prometheus exporter, so we can track these as proper time series. We can get better retention, better alerting, and the ability to define custom metrics. The second part of our monitoring is for the deployment itself. We're using the Kubernetes monitoring suite in Grafana, which gives us a nice, easy, single place to look for a namespace level view across all Renovate pods. At the top, we have CPU and memory across time across the namespace. The periodic spikes map directly to our cron job schedule, which is running 3 schedules over 3 hours each hour. Below that is per pod breakdown, showing average and max usage relative to each pod's requests. Because Kubernetes monitoring uses Loki under the hood, and Loki shares labels with Prometheus, we're able to get a single pod level view that shares both metrics and log data, meaning we can switch quite quickly. For example, say we see a CPU spike, we can get to the logs for that same period much faster. There's no extra configuration needed and no switching tools. When we're running at this scale, having metrics and logs in one place has made the day-to-day and the on-call responsibility a lot simpler. And lastly, alerting. So for Renovate, we have 3 main behaviors that we care about being alerted to. The first catches outright job failures, anything that runs any run that exits non-zero. Without it, we're leaving ourselves prone to only find out Renovate has stopped working when somebody notices a PR hasn't been raised in a while. The second fire is when a job has been running for more than an hour. As we scaled, it was a useful signal for tuning batches, but we primarily use it to catch something stuck, for example, a hung repo or resource pressure. It gives us visibility into repos that need individual attention, and it also indicates to us how well jobs are balanced to complete within our token window. And the third is our deadman switch. If no jobs have been created in 24 hours, we get paged. This catches the scenario where Renovate has quietly stopped running without any individual job ever failing. And it's worth noting these are the Renovate specific alerts we've added. We also get Kubernetes level alerting from our infrastructure monitoring, killed events, crash loop backoffs, any pod or container activity, and the combination gives us the full picture we need. So yeah, that's the wrap up for the slides. We're going to just give you show you how this looks in practice.
Yep, sure. So demo time, yay! Let's see. How do we go? How do I go to the? Come on.
Change the mouse context for that.
What do you mean?
Move the mouse.
You do it. Want to do it?
There you go.
But then how can I control it from here then? Huh?
You're gonna have to change the mirroring, I guess, to that.
Mirroring. Sorry, 1 second. How am I going to do that?
So settings displays.
Yeah, sorry about that.
It won't be a demo.
Yeah, awesome. Thank you. I don't know if you can see the screen okay. I hope so. So this is K9S. We're going to use K9S for the sake of simplicity to show you everything we talked about so far. So as you can see here, this is an overview of the cron job. Sorry, let me make it a little bit bigger. Yeah, okay. So this is an overview of the cron jobs. As we told you already, we run all the updates in batches using cron jobs. So, for example, this is named Renovate Self-Hosted Schedule 0 Batch Job 0, which means that it's the first batch job which runs in the first scheduled Renovate job, which means that we go down to Schedule 0 Batch Job 19. All these 20 jobs run in the first schedule, and when these are done, the next hour you have another batch of another 20, and then you have another batch of another 19. So for the sake of simplicity and like for the sake of the presentation, we have also created this Renovate self-hosted test job, which we are going to trigger now. And while this runs, I'm going to manually trigger this now, and while this runs, I am going to show you the config map. So if I scroll down and go to the config map for this cron job, you can see all the configuration options that we use in our global config. So this is our global config. This means that every repository that runs in Grafana, that exists in Grafana Labs runs on this config, and this is enforced by the security. We work with security team, we work with the security team, and we came up with this config. So as you can see, there are stuff like caching private packages. We don't allow any custom commands, as we talked to you about before. I'm going to come back to this in a little bit, to the extents bit. And we also false disable plugins and scripts, so nothing funny runs in there. And we do other stuff like minimum release age, which means that if a package has been released in less than 3 days, don't merge that because it's probably not 100% safe until it's like properly tested. We have OSV vulnerabilities, vulnerability alerts enabled, and other stuff like you can auto-merge vulnerability alerts as they appear. You don't really have to wait until someone reviews them if they are critical. And you can label them, you can label vulnerability alerts or create groups of vulnerability alerts if you want. So this is the config map we use. And oh, yes, sorry, I forgot. the extends part. So this is the shared presets bit we talked about just before. So we, again, enforce these presets as best practices presets to every repository, but we give teams and repositories the option to opt out of them, because we believe that opting out of them instead of like giving teams the opting in option is better, so we can know who does what and why, and like every opt-out case should come through a PR, and like teams should be able to justify why. Then if I go back and I check the pods and scroll down, I'm going to talk to you about the error. So you can see the self-hosted job manual runs, and if I go check the logs in K9s, you can see the logs appearing and like Renovate running. So this means that probably, if it finds dependencies, it's going to create PRs for our test repo SCaLE 23x Renovate demo. And about the other ones, you can see some errors here. These are like the actual Renovate jobs we run in our real repos, both public and private. So when something fails, it either means that it got some rate limiting, not GitHub rate limiting because we have taken care of that, but some rate limiting somewhere else, or maybe, I don't know, GitHub is down, or maybe I don't know, some private registry is down as well, and they keep on erroring. But as you can see, if this errors, because Kubernetes, right? If this is failing, then it gets spinned up again, and it runs. It's the same job, yeah? Yeah. Schedule 0, but job 1, it runs again until it succeeds, basically. And if, as Phil mentioned before, if it doesn't succeed multiple times, then it means that a repository doesn't get enough PRs in a certain time frame. So we're going to get alerted because we don't get enough Renovate PRs in repository A. So we can jump in to fix that. If I scroll down, this is still running. Is it? Yes, still running. And I wonder if, so this is the, sorry about that. This is the repository we created for this purpose. So in the pull request, you can see, opened 1 minute ago. This means that Renovate found some outdated dependencies and created updates for all these dependencies. If I go and click on a random one, let's go to this one. You can see a really nice PR with merge confidence, which means that other repositories have been using this version for a while, so it's probably safe to merge. And you can get stuff like release notes, all the release notes, everything that happened since that has been updated since the last version. And also, last thing I would like to show you here is this button. So Phil talked to you about the webhook listener. So this is an extension of Renovate, some extension we created. So if I go and click here and check that box, we should get a message saying that Renovate is updating Renovate is updating, is rebasing the PR. This is really handy when it comes to outdated dependencies, or maybe there was like another PR which got merged and you get some conflicts. So you click on that button, and then Renovate is processing the repository. So this takes 1 minute to 2 minutes, but because we don't want to keep you waiting, Phil is going to continue showing you the dashboards.
Yeah, so to just give you a little view into the observability tooling that we mentioned, this is the Kubernetes suite. Make that a little bit bigger for you. Within the Grafana instance, it's the opposite scroll. Demetrius just kicked off a test job here. We can see how it's running. We can click into more drill down on it. We can see an overview, general resource usage, pod count, and what's going on here. The most useful part of this for us really is having everything in a single place to quickly switch between logs that you can see here. Okay, that's an old pod. That's why. Let me refresh that. Okay, the curse of the demo. Okay, here we go. So this is the one that's currently running. The most useful view for me is this single inline here that we can see exactly the pod name, the status is already succeeded, it's finished running, which we saw from the PR activity, but now this is totally complete. Because Loki and Prometheus are sharing labels here, we're supporting to be able to directly follow through to pod logs as well, which has been super handy. And that's about it for that. And the other one to mention here is our Renovate dashboard. So this has been the main place that we've been monitoring uptake and operational health. So on the left here, we're pulling the 1.72K repos, the amount of repos processed within the last 2 days for our time window here. Or we're pulling this figure from success log lines and counting those. The total security PRs count is one that we're calling GitHub API using the Infinity data source for directly. And we also list which security PRs are open for quick access. We have a little on operational health. Again, more resource usage, app limit usage. Since caching, we're now sat around 40% of our limit. And then, yeah, probably the other one to mention that's been particularly useful is our repository process and duration timeline. If you are self-hosted Renovate, or even if you're not, and you can get these metrics, it's been particularly useful in troubleshooting anything long-running. You can see here straight away that we've got a couple of outliers at the top. This is an example dashboard. This is a subset of our org's repos for the sake of the demo, just the public ones. And Grafana there is running 18.3 minutes, or average around 18 to 19 minutes. We know from knowing this repo, knowing the complexity of its dependency tree, that this is expected for Grafana, but in previous cases, we've had some shooting up to like 40, 50, even over an hour. And straight away, we can go to that team, we can find out more information about the context of their code and their dependency tree, and we can work with them to see if it's actually something that we can help improve, or we essentially just have very quick recognition on that. I guess the last one to mention is the management overview. So we mentioned the PR times and security merge times. We track those here. We track the types of dependencies, and we're tracking the rate of change over time as well. So you can see it's going from days down to hours over the last 90 days. So I'll just flick us back here. So we can see that this rebase is completed. That took about 2 minutes, just less than. So yeah, that's how that's worked. Let me flick back to Grand. Okay, so yeah, that's essentially us, but we just wanted to wrap up with this. The Tempo team at Grafana reached out to us to share that since adopting Renovate, their CVEQ is at 0. This was really nice for us because this is the outcome that we've wanted. It's not the tooling, it's not the automation, it's that our teams have been able to effectively reduce their backlog of security debt with minimal overhead. So yeah, we hope today's given you something useful to take away, whether you're just getting started with Renovate or already running it and hitting some of the same walls we did. And please come and talk to us if you have any questions, or we can take some questions now as well. Thanks.
Who was first? I don't know. I think at the front. Yeah, please go ahead.
Thank you for a great talk. We use Dependabot, but there's a lot of still manual review process to make sure dependencies look great. I'm kind of curious about with this fully automated flow. We've had cases where dependencies upgrades introduce a bug, there needs to be rollback.
Want to take this one? Me? Okay. Yeah, I mean, of course, there are many times where you like update something to a new version, something breaks, you don't know. So this is why you have to have sufficient CI checks, I would say. So every time there is a PR created by Renovate, you have to make sure that all CI runs as it runs on every other PR. So if the PR passes, it's like if a PR that got created from Renovate passes and you merge it and it creates a bug, this is like any other bug you introduce from your code. It's not specific to Renovate, basically. But then, yeah, if it introduces some bug which conflicts with your code and then you have to fix it, you either roll back to the previous version or you fix the bug directly. But if it's a bug which got created by in the library, in the dependency itself, then you can go file an issue or you can wait until the new version comes out. And this is why all the release notes in the Renovate PRs are really handy, because you can see exactly what changed. And before you merge the PR, you can go to that specific place and see, oh, this is changing that. Am I affected? Am I not affected? And you can judge. We have created the auto merge strategy, but it's really, really, really complicated, not trivial at all, because every time something gets updated, you have to be careful that you're not going to mess things up. Even if everything passes, of course, it's like any other bug, really. I don't know if this answers to your question. Yeah. Next? Yes, please.
Was it easy to decide on going the fully automated route, or were some teams or then sort of resistant to it? And like, how did that discussion play out in planning and then after that?
Me? Yeah. We started before Renovate. In Grafana Labs, we use GitHub. Yeah. So Dependabot was the obvious solution for us. The thing is that some teams were using Dependabot, some weren't. So we needed to find a way to enforce dependency updates and like security updates across the whole organization. Of course, we have like hundreds of teams maybe in the engineering, not hundreds, but like many teams in the engineering department. Some teams, some repos were more hard to convince to bring them over to Renovate than some others. The thing is that we needed something to work the same for all repositories, and this is why we created a global config, which is something you cannot opt out from. And I won't lie, it was hard. There are some repositories which are huge, and in order for Renovate to run on them, you need like 30, 35 minutes, for example. There are some others that need like 1 minute or 30 seconds or whatever. We didn't really find resistance, I would say. It wasn't like resistance, but there were second thoughts. Dependabot works for us. Why should we move to Renovate since Dependabot works? But the answer was because we need something to work for everyone, and there shouldn't be a way for anybody to opt out of dependency updates in general. You can opt out from some certain settings if you want to, from the configuration, but the end goal again in Grafana Labs was to make sure that all repositories, like the moment they get created in the Grafana organization, pick up the global configuration as we have set it, as the security squad wants it, and yeah, that's it. But no huge resistance now.
No, it got a lot to add to that as well. It got a lot easier the more we communicated it as well. The more we communicated how flexible and how custom presets, for example, teams start to see the value in what they could set themselves, and even moving over from Dependabot. I think it was one of the back.
Yeah, sorry. Yeah, go on. Both. No. It's both. It's both security vulnerabilities and just dependency updates. Yeah. And security vulnerabilities. You get. It's essentially the same mechanism. The only difference is that in security update, in security vulnerability PRs, you get like this big PR description with the CVE, all the descriptions. Steps to reproduce as well, if you want to reproduce the vulnerability, and all that. So yeah, it's both. And
how far did you take it? Is it just a patch version or patch minor?
It's everything that comes, anything that comes first, I would say. But you can set it up in your own repository. You have the global config, but in your local config, in your repo, you can say, I don't want patch updates, patch bumps. I only want like minor or major bumps. You can set it up like it's completely doable. Yeah, and some teams do it already, I think, because it's a great tool. Like updating dependencies in general is great, but it can be really noisy if you don't set your own rules and you let it create. For example, one thing we've seen is we have set up a limit for PRs or branches created by Renovate, if I'm not mistaken, and we have set it up to 5 or 10, 5, I think? Yeah, it's 5. And some people are like, even 5 is a lot. I don't want 5 PRs to get created from Renovate all the time. Some people are like, just remove the limit and I just want all the updates in the world. And there are some people who get some teams who get 35 PRs in one single Renovate run. So it's just a matter of preference, really. Yeah, please.
No, it's sequential. So Renovate separates a type of dependency update to a branch level, and then once the next version from the current is updated, then it will continue. It depends if you can configure all this. You can add it, you can set it to get the latest at any point, but then that works in conjunction with the minimum age as well.
Yeah, and you can also configure Renovate to create a PR with groups of dependency updates. Like have one group that has to do with Go updates, for example. So instead of getting 5 different PRs with Go updates for different Go libraries, you get one PR for Go updates, which contains 10 different updates if you want. If you don't want to, you can have separate PRs. It's whatever. It's the reason we chose Renovate is because it's highly configurable. Sky is the limit. We created the webhook listener. You can do whatever you want with the listener because you host it yourself. No worries. Yes, please. Sorry. Yeah. Do you want to repeat the question? Do you want to repeat the question? Because I think it got louder. Do you want to do it? Repeat the question?
Sorry, we can use the microphone.
Yeah, because, sorry, it's... Can we use the microphone?
Yeah, we probably should have done this from the start. But
I hope it works.
Hello, thank you.
Oh, awesome.
Yeah,
yes.
I appreciate the talk, and this is my first time hearing about Renovate Bot, and that seems awesome, useful. So my question was, when setting parameters for automated dependency scanning, at what point do you consider a dependency sufficiently aged? And I assume that's as a function of your security policies. And at what point do you consider a dependency stale or vulnerable enough such that the top-level parent package needs an alternative or maybe a rewrite of the stack that you're working on?
So for...
It's a little off topic there.
No, it's fine. So we have set a rule of minimum release age for a dependency to be 3 days. You can set it to whatever you want to set it. So this 3 days time frame came from the security department. I think it's some sort of a magic number. I think many companies use 3 days, and I think it's the default in Renovate itself. If you go check out the Renovate docs, I think it says that the minimum release age by default should be 3 days, if I'm not mistaken. So what happens is that if you set that up, if you set minimum release age to a certain number of days, let's say 3 days, what happens is that you still get the PR you still get the PR from Renovate, but you have a check, a GitHub check or GitLab check or whatever you use. You have a check pending saying like stability days, and it's still pending until it's stable, until 3 days have passed. And now you can make this check mandatory in a sense that, you know, if it doesn't, if this PR is open for less than 3 days, I mean, you're not able to merge it, otherwise merge it. Or you can do it on a completely optional level. So teams can decide if they want to merge it, if they're safe, like if they feel safe to take the risk in a sense, or if they want to wait for 3 days. That's the first question. The second question was
around staleness. I guess that's mostly manual at the moment, but it's up to each team to, if they've not been keeping on top of new updates there, and they're coming to a fairly old update, they can just close the PR and allow Renovate to then run the next. But we don't enforce that at a global level, do we?
No, not really. But if you get a PR from Renovate with, say, an outdated version, and you keep it there for 3-5 days, and then there is another version of the same dependency, the same PR gets updated with a new dependency. So it's kind of hard to have not hard, but it's kind of rare to have a Renovate PR stale, because for every new version, the same PR gets updated. The title gets updated, the commit message gets updated, everything gets updated. So now, yeah, I don't think we do anything else about that. But you can absolutely configure it like to the level you want.
Thanks.
Yeah. Any more questions? I mean, we're going to be here if you want to talk to us, or we're going to be at the Grafana booth after 2 p.m. if there are more questions you want to ask us in private. And I think that's it. Thank you very much.
Test, 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 test. Hello. Oh. Test. Nope. Test, test. Oh, I guess I can't adjust it from here. Oh, yeah, I don't wanna. I think. Hello, hello. I can test this. I can test the other one.
No AV person shows up in the next 10 minutes, I'll go mess with the board.
Oh, okay. Yeah, thank you. Test, test, test. Pop, 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 pop. Okay. Loki, 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 Loki. Test. Uh, I'm not sure. I wonder if this sounds good? Okay. Oh. Nope. There we go. Hello. Hello, everyone. I think we can start. Hi, everyone. How's how's everyone's day today? This is actually my first talk at SCaLE, so please take it easy on me. Well, welcome. Today I'm gonna be talking about how we migrated to Loki and some of the lessons that we have learned. My name is Vin. This thing is annoying. My name is Vin. I'm a senior software engineer at ZipRecruiter. I do basically a lot of platform engineering, SREs, DevOps works. So yeah, all the fun. And at ZipRecruiter, we're the #1 rated hiring site that helps connect millions of people with all companies of all sizes. So how many people know what Loki is? Raise your hands. Oh, great. I think the talk is over. How many are running in production? Oh, okay. There's a few of you guys. So one of the big things that we see when running a logging system is that sometimes your bill of your logging SaaS bill is pretty high, and executives are complaining why it skyrocketed over the past few years. How many times have you seen this? Not that much. So with our current problem, our logging bill was basically competing with our AWS infrastructure. We were already paying a lot for logging, but to do everything what we actually wanted, it would cost even more. We use LogZL as our vendor, and they serve us really well. Before that, there were some other infrastructures that we had set up prior to that, and I'll tell you the rest. What you'll learn today will basically either evaluate whether Loki is a right stack, right fit for your stack, some trade-offs, and some practical Kubernetes scaling on how we do cost automations on patterns, and some budgets for your migration. Before we can go through how we migrated, we can talk about how ZipRecruiter's logging pipeline over the past years. It's actually not that crazy. We were running Elasticsearch hosted. We were managing it practically a full-time job. Lots of JVM tuning, shard management, upgrades. So we moved to a managed SaaS vendor to get out of that business and basically focus more on building products. Engineers could search their logs without babysitting a Elasticsearch cluster. I'm not sure if you guys have managed Elasticsearch clusters, but it's not fun. It was the right call. We scaled over 1,500 services, and within our budget, we ended up back with Loki. We come to a full circle. Loki didn't exist when we first needed logging at SCaLE. We worked with what was available during that time. Times has changed. Kubernetes matured. We were fully in Amazon, so S3 became more cheaper. And Loki and the Grafana ecosystem was already emerged. And we had a pretty stable pipeline to deploy to Kubernetes easily. Yeah. Our current logging pipeline, basically, we had about 1,400 services. That's across 7,000 pods. We were limited to 2 terabytes a day of just logs in our production tier, while the rest of the tiers were 5 terabytes across all environments, production being the most. We had 2 kind of pipelines. One is going to our logging vendor, And then the second was going to Athena. We did this way because we only had a short retention to our login vendor because the cost was too much if we were to go over our budget. We had Kafka in the middle just to handle throughput and real-time log streaming, which helped us a lot when sometimes our vendor goes down. Oh, a little dark. So here's the pain points of currently what we had at ZipRecruiter. Originally, we had a 4 terabyte per day of quota, and then initially we had to cut that down to 2 terabytes. All our logs were sampled. We had to alert some teams that they were going over the budget, and which was kind of painful to tell that they can't log too much. We also only log out specific types of logs, mostly errors and sometimes warning, and everything else was just not showing up in Logs.io. Our default app quota is about 10 megabytes per hour, and we had alerts off of that as well if a app was logging more than that. And creating new apps was a pain. We had to format the logs in a certain way to get it into our logging pipeline. And the big thing was the retention was only 7 days. We only had 1 full day of just Kubernetes cluster logs if the developers want to look from there. But in our login vendor, we only had 7 days. And as we scale more, we also see that the cost of logs goes up more, and we had to deal with the pain of just sampling, constantly sampling. And this is where Loki comes in. This is a quick short what Loki is. It's a open source log aggregation system by Grafana. The simple ways to think about this is it's like Prometheus, but for logs. How many of you guys use Prometheus? Awesome. So it's basically using the same labels. It only indexes metadata, things like namespace, log level, container names, and not actually the log content. The log content gets compressed and stored in an object store like S3. This is what makes it more cheaper for us. And if your team already knows PromQL, LogQL is actually really familiar. Same label selectors, same aggregation patterns, and then some of the extra steps to filter down and parse different logs. And to interact with it, you can go through Grafana or use the log CLI. So why not other vendors? We could have chose so many other vendors to basically deal and make a compete with other costs. Hosting another Elasticsearch would be maintaining two separate platforms to visualize your logs and find logs. We were already using Grafana, and most of our metrics is already connected. Loki was a natural place for that. Self-hosting today was not what it was years ago. We had more stable build systems, and deploying to Kubernetes was actually really easy for us. We deployed Grafana through Helm, but we actually convert that into manifest and then modify that through customize to make adjustments. We don't really love Helm that much. This gives us full control over what gets deployed during runtime. We do our tuning from there as well. And the day-to-day operation is pretty straightforward. The real work was just tuning after. And then, so this is more of the reasons. Cost, same single pane of glass is a big important piece. And there's some mental models of we had to change, like labels, how it is very native to Kubernetes. Running Elasticsearch, that means no more tuning your JVM heap, no more shard management, and mostly the read path is mostly stateless. Loki scales pretty horizontally and just by adding more components. Self-hosting was pretty easy with just automatically adding some automatic scaling for Loki. Here are some of the trade-offs that we considered for Elasticsearch versus Loki. Every logging system makes the fundamentals trade-offs. One of the side notes, on the side that you have full index, full text indexing, like Elasticsearch, while every index is filled in every log line. That means you can search instantly in your Elasticsearch, but that comes with a cost. It's pretty expensive. On the other hand, Loki, it only indexes metadata, namespace log levels, and a handful of other labels that you choose. The actual log content gets compressed and stored in S3, which is a big plus. And the number one thing that trips people up is that here nobody talks about the labels actually maps directly to your Kubernetes topology, which makes it more easier for engineers to already think about their services, like just choosing the namespace and pods. And once they make the shift, their queries become more intentional and actually much faster with Loki. And then here is like a quick rundown of like what a Loki log looks like. You have your timestamp labels and your selectors, and then the contents of the log line. The context log line is not indexed and is compressed into S3 as chunks, in which for Loki, it only scans after you narrow it down by labels. And then, so here's a quick rundown of Loki architecture. Basically, you have your write path. Distributor validates incoming logs. Ingester builds and compressed chunks into memory and then flushes them into your object store. The root path is basically the query front end that splits up large queries from Grafana. So this is like going from the Explorer or certain logging or Loki panels that you use. And the courier front ends, they also execute your logql against the chunks, and there's different caching mechanisms, like which is used mcache, and the key insight is that the write path and read path scales independently, so you can add more couriers without touching your ingesters. And this is what makes auto-scaling practical. It's much more cleaner version. And this is how we start to wire things up. Before that, there's different ways to install Loki, either the monolithic, simple scalable, which is going away in Loki 4.0, and distributed mode, which is what you saw previously. And that's what we have decided to use based on our log ingestion rate. I'm not sure you guys can read this, but basically this is more like a zoomed in of our current setup. We are using bloom filters, which I will talk about later. But the short version is that the couriers in which the chunks that to skip that you don't have to scan everything, that makes it much more faster for bloom filters, which also solves one of our problems of wildcard searching. And zooming out, So now we have two of different logs ingestions. Basically, we were running, we replaced our file beat, which was kind of outdated, and we wanted to more flexible and that can ingest more logs at a higher rate, which is Vector. It's basically built in Rust and doesn't do any kind of no garbage collections. And the thing is that it can take different kind of sources. So we're running Vector Agent as a daemon set, and then we run also a Vector aggregator to also get any other non-Kubernetes logs. Our CI/CD is mostly in GitHub Actions, so we export logs through that way. We still use Kafka because that's helped us to, in case if we do have issues with Loki, it's still there to at least ingest the logs if there's any issues during the queue. Here's our playbook of how we started our migration. We installed Loki and Vector on the first day with just minimal configurations based of what we thought that would make sense with some small tunings. We use Vector as a way to get metrics on how much logs we get. I can tell you later, there are some weird metrics that Loki emits that seems to be not incorrect on finding your total log ingestions. And we use Vector to also parse our structure logs, which helps turn them into labels. This is actually a way to filter out what actual labels you want. And we also drop some logs related to some certain namespace that we don't want to be including. And Vector, it could be any other log forwarding agent, but we chose Vector. We still had to run two logging pipelines because we were still having weird. We have some data pipelines in our old logging pipeline that was very dependent on the current setup, and we didn't want to touch that and migrate that into Loki because that causes issues with some of our downstream consumers. So that goes to some data pipelines to related to Spark jobs, and then some weird ways of creating dashboards through logging. We contacted our developers about this change, communicated out and tried to reach out, find understanding of how we can change or stop doing what they were doing with the data pipelines using their log. We initially find out beta users to validate that logs are working. And the feedback was very important because there was a lot of upset folks about using Loki in our initial run, and we tuned based on what we found. There was a lot of people were still using our login vendor as a dashboard that they had set up long years ago, and it was still working. We had to migrate that into Grafana, and then we created a lot of documentations because since this was a big culture change of going from Elasticsearch to Loki, which I'll explain later. And then we turned off we eventually went off of our vendor. Okay, so what broke? Things on the first day, I guess second day of rolling out and having beta test users was not good because they actually did test out our limits with Loki. Going from a bunch of pods kill, and a lot of our clusters were going down in production. And this is during when we had we were still testing out Loki, but we also learned that searching in Grafana Explorer wasn't that good. During that time, we were running on an older Grafana version, which we didn't have the Loki drawdown, which was unfortunate. So a lot of folks were very confused on how to find their logs through the Explorer. And learning LogQL was also a new thing, even though some folks might have known or might know what PromQL is, but it's still also very confusing for folks. And we had this is where the wildcard search started happening, where someone ran like a regex match to across all our namespace, and it scanned 43 terabytes, and eventually it timed out and broke our cluster, and eventually telling them that we'll just restart Loki, and obviously that was a quick fix, but that didn't make the developers happy. And this was a common pattern across our developers when we migrated to Loki. The problem isn't Loki; it's the Loki that Loki requires you to think about your query differently than Elasticsearch, and the message wasn't clear. So here's some like stripped down of Slack messages that was sent to us when we first migrated. I'm trying to like Loki, but it feels like an order of magnitude of 2 worse than logs.io. And this is the first week. It's really slow. I tried querying over 15 minutes and 3 hours and errored out. Did I mention it was slow? It was painful, and people were searching build IDs, request IDs, just through the wildcard search, and that did not help out at all. There was production incidents that arises some of the issues that we were seeing. Teams open up Grafana during production incident and don't know how to write LoQL. Mostly a lot of global searches because normally that's what they were doing in our login vendor. The worst time was to learn a new language is during an outage, from what we know from during postmortems. Engineers has been using our old login vendor as a poor man's distributed tracing, as searching for request IDs through like our web servers globally. Loki can't do that without specifying namespaces, and you have to meet developers where they're at and so this is where we started to think differently. Wildcard searches are okay. It's never a bad thing. This is like a fundamental mental model shift that we see in Elasticsearch. You can search strings across everything, and the results come back pretty quickly because there's like full text index. But in Loki, is not like that. You have to pick your labels, namespace, or log level, or a pod, and then it finally decompresses and then scans, and then match your filtering. So I know that when we started migrating, a lot of the folks didn't read our like migration guide of to Loki, and that was a big pain. And I think we were actually looking different ways of how to improve that during that time. And then another thing is that even though we migrated to Loki, we thought that the cost would go down, but it actually went up. We had our AZ costs increase significantly, and one of the reasons that we found out was that one of our ingesters that was talking to our logging forwarder agent were on different AZs, and eventually we fixed that. So yeah, we're just burning money in AWS. Recently, even though kind of contradicts this talk, but we also found out that even though we set up Loki to how we thought it was, but we overestimated the resources that we set, which was also burning more money. So it's a one-time setup, but in reality, it was mostly a lot of tuning when we migrated. And this is what I was talking about earlier. We needed metrics to find how much logs we were getting. And one of the important things is that this metric that Loki emits was actually giving us the wrong right size for our cluster, which goes back to there's like a cluster sizing that Grafana shows that we followed. And that seems to be throwing us off based on this metrics. In prod, we were expecting that we were getting 4 or 5 terabytes a day, which is a lot compared to just 2 terabytes originally that we expected. And there were some big known issues related to this metric, and it kind of threw us off a little. This is the part where that no one kind of tells you that you keep tuning Loki clusters. We went through different tunings for the ingesters, tweaking some of the like the rate limits and all that, and the compressions, changing some of the data store, switching to different AZs. Originally, we were running an on-demand because we thought that we didn't want to have Loki go down during spots, but that kind of raised up the price more. And then eventually, we migrated Loki to spot instances, except for the memcache pod. We tried to. There was a lot of tweaking with Grafana's data source timeouts, and that helped us a lot because some of the queries that the users were running, they would take at least almost 3 to 5 minutes, which is not good. And some part of that was related to their wildcard global searching, and so we were trying to optimize that. And the big thing is using bloom filters, which I will talk about later, but it helped us a lot with trying to find like global searching, like request IDs. And then another thing was chunk storage tuning. We basically started increasing to flush more to S3 while the default settings was a little slow. And then so there's this right sizing table that Grafana has that I was mentioning earlier. It breaks down exactly how much replicas and how much CPU and memory that each Loki needs based on what logs you are ingesting. Like I said, we started off with the default Helm chart values and slightly increased it in the beginning. And that was during when we had beta users, and so the load was not that crazy high. And we were still kind of filtering down on certain namespaces to just for like decrease cost during our beta testing. And then so the ingesters was definitely undersized when we started running, so we were hitting a lot of ooms. We ran out of memory. And one of the key recommendations that Grafana mentions is that when you want to run small as possible for your carriers, so you can horizontally scale. And then so we initially had a max of like, I think 20 couriers and ingesters. Actually, 20 couriers and then 10 for the ingesters. And that was the wrong way to do that. And so my advice is start sizing based on this table, but be more flexible on querying up. So we eventually start querying up. The max is like to 200, I think, but we slow it down to a half of that. And we were using horizontal pod scalers for queries and ingesters. Another hard part is storage. There's a few knobs that really matters. You want to flush frequently, and how often the ingesters push the chunks to S3. The more frequent flush means smaller chunks and smaller S3 get requests, which lowers the memory pressure. And it's also like a faster recovery when restarting Loki. We tune more frequently for flushes because ingesters stability matters more marginally with S3 costs. The Mcache external store was not a out-of-the-box setting that comes with Loki Helm charts, and that's something that we manually enabled, and it's also mentioned in deep within Grafana's docs that this actually helps a lot with caching. And we use local MVM SSDs as an overflow for our memory. And right now we're setting around 550 gigs for our cache capacity per node. And that's why the chunk cache can't run on spots, because it's going to take a while for it to rebuild. And then we still running the single compactor that Grafana recommends. And basically it just merges small index files and enforce any retentions that you have set. Which is our retention was 90 days for Loki. This is a big issue. We put pods and nodes as labels because they felt more natural as the metadata. They're core Kubernetes concepts, and of course you can filter down by pods. The problem is that every unique combination of labels creates a new stream in Loki. Pod names are unique per replica, and so a deployment with 50 replicas can create 50 streams for every container, for every restart. During peak traffic, autoscaling spins up a new pod constantly, which creates new streams and adjusters to hold memory. And we were already filtering what labels should be ingested through our logging forwarding agent. But we noticed that once we migrated pod, node, and request ID and build ID out of the labels, this into structured metadata using the Bloom filters was the way to go. And the results was faster searches using like request ID and pod and node labels. So Bloom filters, this was like the biggest, I would say not biggest lift on global searching, but this is still experimental from Grafana. This is how we were addressing it. Basically, Grafana says Bloom filters are basically like finding a needle in a haystack, and it literally is. This, even though request ID is too high of a cardinality, so searching for that kind of request is really painful and slow. And engineers really wanted to search through request ID, even though they were using it as like a poor man's tracing solution. But with Bloom filters, it made it much easier to search that kind of ID. And we had to manually increase the persistent volume for each of the Bloom components, which helps a lot because we run it every day to, I think, about 8 hours on those IDs that we set. And then so the combining with the structured metadata for all the fields like the pods and request ID, that was the gap between the Loki and Elasticsearch with developers issues. So there's a few things that we also did. Loki also use it, especially the operational dashboard. And we also added SLA SLAs on top of our cluster. And then so this is an example. So every instance I described, like the 40 terabytes query, the cardinality trap, the OOMS kills, we debugged them all through Loki mixing dashboards. They're really helpful. We added SLOs, sorry, not SLAs. On top of that, treating your logs logging platform as like a production service for our customers, for developers. And one of the great things is Loki comes with a canary pod that can test your logs. We didn't run that initially, but it is useful if you're running and testing your logs. There's a feature that you can enable through Helm. So, was it worth it? Was it worth migrating to Loki? I would say definitely yes. We were getting more logs than what we expected. We were getting about 7.5 terabytes per day compared to just sampling down to 2 terabytes. We removed a lot of the alerts that were paging teams that they were going over their log usage. And so across all the tiers, we were getting about 15 terabytes. So we also like ingest unstructured logs as well. And that's go through our vector aggregator. And about the migration, it's about 50% of the volumes that increased it. And we were suppressing production logs a lot, which was because of the costs. And so now it was way better than we expected. And then so here's like a before and after. Like I said, we sampled, now we're taking all logs. The retention is much longer now. We set to 90 days because this is what we had originally set for like kind of like certain audit logs, but now for all the tiers, we set 90 days now. We still are running Athena with the Athena pipeline with Loki, so we can still go more than 90 days in Athena if you like searching in Athena. And of course, we removed the separate search systems. Now everything's in Grafana. People have integrated Grafana into our catalog. We use Backstage, so a lot of the apps developers can just go to Backstage and can see their metrics from there and logs. So it was a pretty nice thing. There was some, I would say, having something self-hosted was what we prefer more because we can control the costs and make it more secure as needed. And so developers were happy eventually. Even though I can't share exact numbers, but I can tell you that logging costs was, it's now like a fraction of what originally we were paying for. And we ship specifically more logs and longer retentions. The cost story isn't just that Loki is cheaper, but we ship all logs now. That was really the big thing. We get more features out of it. If you're evaluating this, the math works out roughly at par or less than you're paying for your vendors. but there comes with the cost of that. Making it usable, we get asked so many times during the migration about how do I find logs still. And previously, we created a bunch of documentations, and obviously no one reads that. And so people still hate PromQL, and now they have to learn LogQL, so that's even worse. So what makes it better? We eventually upgraded our Grafana and including all the nice features. The drill down was the most plus positive thing with the developers, because they can just go there and then search for their namespace, and then they can explore from there. But some folks didn't like that. They would rather have like a centralized dashboard. So we created a actual dashboard with all the fields and labels that we included, and so the developers can just filter down from that way. And the logs is already formatted. The log line is already formatted to what they prefer. And then we include some metrics. And then that was a big plus. But why not go more further? I mean, it's 2026. We're all using AI, or most of us maybe. And so there are some options. Grafana offers a MCP, which is like let's allow you to have your AI assistants or LLMs talk directly to your Grafana. It works both locally, on-prem and cloud. And one of the great things about that is that it can query logs and metrics through Loki, and any kind of metadata. Like you can just ask my app, this namespace is failing in production. Like how do I can you find me what's the exact error I'm getting, and it'll just come with the actual response. Instead, you have to go through the Grafana Explorer. But there's some caveats with that. We had some legal issues with running certain MCPs, so that was still on hold. So we eventually created a app triage skill for Claude. We're heavy usage of Claude, so we created a skill for that, and basically let Claude understand how we structure our labels, and it can just create the queries for developers to use. They can use log CLI or copy the queries over to Grafana. Another thing is that we also created a Slack chatbot for our hackathon, and it has access to our documentations, to all the Loki documentations, and to our GitHub repo. And so you could also ask our chatbot how it would how did they debug their app, and it will return some pretty useful log QL that they can just paste over. The only thing is that we haven't connected to Loki to our Slack chatbot, but that's maybe more a feature invitation. What we learned. These are the 7 lessons that we have learned going through the migration. Number 1 is Loki is not Elasticsearch. Loki shifts the cost from writes to reads. The ingestion is a lightweight and cheap, but the keyword has to brute force the chunks. Training your engineers on this mental model shift before you flip the switch, or not after. Labels are your schema. Lower cardinality helps a lot. And originally we thought pod and labels was a good label indication, but when Loki introduced structured metadata through the Bloom filters, that made it much way better for the developers to search those kind of logs. 3, optimize write first. This is kind of counterintuitive. When you optimize your write first, larger and fuller chunks means fewer index entries, which means also faster queries. But then that means tuning your chunks like configs, and you're constantly tuning to where you find the right balance. And this was one of the biggest tuning improvements that we did, was this, the chunk cache. 4 is the Grafana sizing table. Even though it's a good baseline, which we highly recommend. Obviously, not running default settings is not good in the first initial run. We were on defaults for weeks during the beta testing, and obviously that killed a lot of the pods. One thing to add is that we did have like LLMs to help us constantly tune Loki based on the charts, and it seems to help a lot. So you were like pass that chart and some data about how much logs you're ingesting, that made it pretty simple to use. And then another thing is you gotta budget for developer experience. I think that was the most painful thing for developers. You obviously don't want to hear that Loki is slow. Why do we migrated? I think even though docs and dashboards wasn't helpful, but eventually like tools like the AI LLMs, that helped a lot. And the migration could have been done differently. So definitely debug in the beginning with confidence. And then this goes back to the chunk storage, investing in the cache. When you cache hit rate is determined by your query speed, target over like 7%, so cache hit rate. You can find that through all the Loki's metrics that expose, and we have a dashboard on that. I didn't show that, but we were using that as a indicator of when developers are searching in Loki, and we can see all the stats of how long is their queries running, and then like how much of the cache was, how much it was hitting the cache, which was a good indicator to help debug our Loki cluster. And this goes back to using LLMs. It's actually really nice with guardrails, of course. It helped a lot of developers to just ask Claude, hey, like I need to look for this production incident, and based on the logs that I'm seeing, and definitely helps a lot. And they don't have to learn LogQL. And that burden kind of lifted after that. And so it goes back to this. So at what cost? We saved significant money on our vendor licensing, but we invested a lot of real-time engineering hours to get here. I mean, we were a small team maintaining Loki and Vector and our logging pipeline, but the real cost is really about ownership, flexibility, capability, and predictability of when a vendor can change when your quotas overnight, but with the right tuning and troubleshooting issues, it could take many hours with Loki reading docs. On the plus side or downside is that developers are unhappy with the slow changes that we made, and then eventually there was a steep curve for them of migrating to Loki, and then eventually it kind of got better afterwards. So yeah, definitely it took us in the rabbit hole of getting them happy. And so here's the journey. Like we started struggling, costs was spiraling. We weren't getting much logs, and even though we battled the costs of migrating over, we fought developers' experience problems, and we kept tuning and tuning. We came out on the other side with more data, more retentions, and more capabilities that we wanted at a lesser cost eventually. And now our teams are building on top of Loki that we can never done with a SaaS vendor, and especially with production incidents today, a lot of like going back to the app triage skills, it helps a lot with developers to learn that. And there's still more things that we are continuing on with improving our cluster. Loki, Grafana also mentions like using Kata as to auto-scaling your carriers, which is also a plus. Bloom filters, like I said, heavily expressed that it helps a lot with bridging the gap with Elasticsearch when people are searching request IDs. And yeah, like the migration was the beginning and not the end. And so yeah, thank you. And a quick thing is that we are hiring for our team, our infrastructure team. So yeah, any questions? Should I? Oh, yeah, I mean, sure. It's up to you. Yeah, thank you.
Thanks for the great talk. Glad to hear it had a happy ending after the somewhat rocky migration. So I think it sounded like part of it was like just learning how Loki worked, and part of it was like getting it configured for your guys' particular setup. And so I'm curious, like, if someone came to you and said, you know, we're thinking about using Loki, or what advice would you give them so that they could maybe have a smoother experience migrating maybe from a different logging solution?
Yeah, definitely. I would say that you want to get like metrics in the first place of like finding the right metrics of how much logs you're getting, and just the cost of I would say if it actually makes sense to migrate off of your vendor. At first, you know, we were at where we had a deadline of our login vendor, and it was basically just increasing cost more. We had to find the trade-offs of like how much Loki actually costs, and we initially I would say undervalue of doing that kind of cost estimate. We had like a rough estimate of when we thought about Loki, like running Loki in the cluster. And eventually, the gotchas were like we forgot to like change our resources requests and AZ traffic costs, something that to be considered too as well. Yeah.
Thanks. Question, would you say that every developer has to learn some LogQL, or is it more a situation like in each team you need maybe one or two people who can know their way around LogQL and they're going to build the dashboard so that the rest of the team can just find their way around? Like how does that look like?
Yeah. And initially, I think that when we first created documentations on like the difference between Elasticsearch and Loki, we initially thought that learning LogQL was not that bad, but we found out the hard way, and we find out that developers learning LogQL wasn't that bad, I would say, but having developers to learn and understand LogQL, there was a little frustration because they were used to running Elasticsearch, and they can just free text. I would definitely say that no, like it's not necessary now today, especially with LLM. I think we are seeing more productivity with LLM, with users asking how to curate their LogQL, and that helps a lot. And also another thing is that we have like steps of like how to use Loki. The first step was go to the drawdown, which helps a lot because they don't need to learn LogQL, and that's a perfect place for to like discover your logs there without having to learn LogQL. And then Grafana inside, you can transverse that and actually build your LogQL if you ever wanted to go that route. Most of the time, we see developers use the drawdown or our custom dashboard that we built out for them. Yeah.
Thanks for the talk. Really, really appreciated. Really interesting. What is a strategy that, going back, that you're thinking on? How could you have made that developer experience and that transition easier for your developers and get more developers, using Grafana or more familiar with it, or just the productivity overall? How would you have done that, before the full switch over and gotten that adoption?
Yeah. I would say that we probably did like 2, 3 different lunch and learns, and that was just before the full migration switch over, and definitely like that didn't feel like it helped a lot. I mean, maybe it spread the message around, like doing those lunch and learns, and having like a hands down, like maybe an actual workshop that we should have done, like was to have developers sit down and like actually ask what they want. During Slack channels, when we first had beta users, we had them a list full of queries that they want to convert from Loki, Elasticsearch to Loki, and we manually had to like help and translate that for them. So I would say basically it goes down to, I think, spreading the message more clear. And like I said, in probably workshops, it helps a lot more. Documentations, they don't read. And obviously, we don't read documentations. And so, yeah.
Hi, thanks for the talk. So how did you come about to like figuring out the more advanced configuration optimizations, like the memcached for the chunks and the structured metadata?
Yeah.
Did you have to go, to Grafana Labs for that, or did you guys figure that out on your own?
Basically, we eventually found it through Grafana's docs, but it was heavily like nested inside their articles. And so like I will share my slides out, but I did link out some references of all the things that we have found and used, and basically adjust. These are the tuning, like the links that here are what we tune based off of. Grafana has pretty good articles of how like they like scaled Loki different ways, and then there is like a link just for the memcache that we found from a article that Grafana did. So yeah.
And could you explain a little bit about how you do spot instances for the ingesters or whatever? Is that like behind an NLB, or
We use Carpenter. We use Carpenter, which by default most of our services are running on Spot, but initially we just ran on demand because we were still testing Loki, and I guess that testing directly was still running on demand. Eventually, when we went to prod, or not prod, but when we did a cutover, which we found out that we were wasting a lot of costs. But yeah, we use Carpenter to provision like apps and pods into Spot instances.
Okay, and then but how do you like not lose log messages when they come up and go down?
So the only thing is that it's when we're using PDBs, which is helps with when an instance gets evicted, there's still certain number of pods still running. So yeah.
So maybe you do lose a few logs here and there, but
no, we don't, because we're still running. Eventually, we're still running Kafka, which basically puts in our queue of logs. So our logging agent ships logs to Kafka, and then we.
Okay. Is that documented like by Grafana how to use Kafka in the pipeline?
No, because we basically integrate it within our with our existing pipeline already. But yeah, it's not documented.
Could you maybe help us out with that one?
Yes. Yeah.
Anybody else?
Did your S3 costs surprise you?
At first, yes, because we didn't have like retention set up. I think initially when we ran it, there was like some configs that we thought we enabled for S3 policy lifecycles, like which is through the settings from Loki. So initially we did saw costs of S3 going up, but then once we enabled the config that is like set in the Helm charts, it just dropped immediately. So no, so the cost was not as bad as we thought.
That's encouraging. Thanks.
Yeah.
Thank you. Were you at all tempted to go with managed Grafana cloud, or were you set on self-hosting all the way?
We were pretty self-hosted all the way. I mean, we're running Prometheus Loki as well. Like, so Metric was already going there, and we're already sort of trying to transition to use Danos. So mostly just self-hosted. But we didn't, I would say, like, consider Grafana Cloud or like any other login vendors because we felt like self-hosted was the right way to go. Yeah. Any more questions? Awesome. Thank you.
Nice to meet you.
Thank you.
I know Eric Louie. He used to work with him at Second Spectrum and then
Oh,
Genius
yeah.
Force.
Work with Nick, right?
Yeah, yeah. Worked with Nick, Tyler Lawson as well.
Oh, yeah.
Yeah,
Awesome. Are you guys like on the same team?
yeah, yeah. Me, Nick, and Alan are on the infra team at Genius.
Are you using Loki?
Yeah, yeah. We're using Loki every day, all the time.
Are you using on-prem or?
So we use Grafana Cloud.
Oh, okay.
So 'cause we already had Grafana Cloud a while ago.
Yeah.
Our logging journey was Elastic, Datadog, Grafana Cloud. That's how we
Oh,
did
awesome.
it.
Yeah, I mean, like, most of ZipRecruiter, like, we've been transitioning, but, like, we're mostly on-prem, right?
Yeah.
And we didn't have, like, that hesitation, like, we should migrate to the cloud or anything. And obviously, cost was a big issue.
Yeah, 7-day retention. Geez, that's brutal. And you
Yes.
couldn't even get like info level logs.
No.
That's awful.
Yeah, it was really awful for the developers.
Glad you made it.
Yeah. Hello? Does it work? Hello? You want to use this one?
Hello.
Ooh.
Hello. Oh, that worked. I don't think anyone.
Oh, just give it a second.
Oh.
And then turn it.
Hello? Oh, thanks.
Yeah, it doesn't go automatically. Can you say something?
I think it works. I. No, it is.
Is it? Say something. Hello world.
Hello, world.
I think a bit, but too clear.
Worst case, I'll grab that thing.
Hello, can you hear me? Can you hear it? All right, it's working, right?
Y-
Okay.
Yours is. Hello? Yeah? Okay. Like the moon landing. Okay. You just turn it on and off here. But if we switch it mid, it's gonna. Okay. No, other way. Yep. Yep. On top. Yep. But I'm not sure that one works.
Hello? Hello, hello. Can you hear me? Does it work? It works, right? Hello?
All right, I will go first. All right, thanks everyone for waiting. Sorry for about the wait. We had some technical issues, but like appreciate for like everyone to fix this. So today we're gonna talk about, for this presentation, we're gonna talk about containers all the way down, what we learned running in containers for AI and more at Meta. About the speakers today, my name is Fong. I'm a production engineer here at Meta. I'm with the Cloud Foundation Apps team, and this is my first job out of college. Been here for a year and a half. So far, so good. It's getting a bit hectic, but everything is fun so far. And yeah, this is Sean Hopper, my tech lead. Do you want to introduce yourself for a bit?
Hey, Sean. I've been at Meta for about 8 years. Spoke at SCaLE like 3 times, so it's good to be back. Yeah.
A little bit of quick intro about our team, Cloud Foundation Apps. So we run the cloud native stack at Meta. We got kind of like the bridge between Meta and the public cloud, right? Even though we have our own data centers, but there's gonna be some use cases like for the public cloud. And we do OCI containers, while like the rest of Meta is mostly on LXC containers. About the agenda for today. So the first part would be about what is container. We would try to deconstruct like it's a very like like big ecosystem here. And the second part we would focus about the user namespace and the root list aspect of container, which will be like kind of like the main primitive that we're gonna look at today. And we will try to understand more about like what is the special thing about user namespace, and like how is it like leverage inside the container ecosystem. And the next part will be kind of like the star of today's like presentation, the container in container use case. And yeah, this is like container in container is a very like complex definition, I would say. There are a lot of dimensions underneath of that. We would look into like the rootful and the rootless matrix, and trying to like unpack a lot of the terms there. And the last part will be like probably like the best part of the presentation. We will actually talk about like the use cases that we have at Meta, and like how we solve them, and what is like our approach for them. Moving on into the first section, what is a container? I would try my best to deconstruct that definition. So first of all, containers are not magic. To understand like containers, I would try to walk you through like a series of simple examples and some definition to kind of like build the understanding here. Starting first, we have the container formula. Like like container as a very high level. The first component would be the Linux namespaces, which give you isolation. Linux namespace is what gonna like partition the kernel resources, so each process sees only a designated slice of the system. The second part would be cgroup, which enforce resource control. You would allocate it. It kind of enforces the thing, so you can like allocate, prioritize, limit resources, things like CPU, memory, or I/O for process groups. And the last one would be overlay MS, the union file system. Overlay MS are like onions. They have layers. So so it essentially merges a read-only lower layer with a writable upper layer. It enforces something called like copy on write mechanism. So it ensures that what changed always stay in the upper layer, and like the lower level will always be like read only. I think this is one of the things that like makes like OCI Docker container really successful, because of like combined with this capability, and it has a really good like distribution system through things like through like registry like Docker Hub, Quay, things like that. Let's move into like the first the first example, right? Like trying to understand like the container definition. So we have the PID namespace. Let's try to understand the PID namespace by running like a simple like workload here. Let's assume that we are all like Docker beginners. Like when you start with Docker, I guess we all do like Docker run Nginx at some point in our life, right? So when you do that, you essentially have launched very standard Nginx web server. It looks like a normal process, but is it? To check where is it running, I would do 2 steps here. So inside the container, I would do something like docker exec container, like passing like the container ID and like do ps inside the container. You would see that the Nginx process is running as PID1. Okay, but when you move out that when we trying to do like ps on the host and try to grab for an Nginx process, the Nginx process is actually running as it's not like a PID1 on the host, right? It's just like one of the PID among like thousands other PIDs on the machine. So the key insight here is the PID namespace isolation. Like when you use like PID namespace, the kernel gonna create a separate IPs, like like the process ID space inside the container, and the process inside the container thinks that it is PID1, but it's actually it's just like actually like like this one of the process among like other process on the host. The next stage, you got the container running. You want to do things like curl, maybe like localhost, port 80 to kind of like see your Nginx page, right? But with what you just did in the first step, you cannot see the page, right? You might ask yourself, I can reach my Nginx page. How do I do that? So we would do something like docker run -p mapping port 8080 to like port 80. The command like this one. So essentially, this one gonna create a tunnel to forward the traffic from the host port 8080 to the container's port 80. So the key insight here is the network namespace isolation. The container would operate like it has its own dedicated network stack, isolated from the host. So even if inside the container, like the Nginx process is getting like listened on port 80, but it's not actually listened on the same port 80 of the host, you have to like map it out. And the next one would be the mount namespace. Okay, you got the container running, you can curl like the Nginx page, but now I want to serve my own HTML page. Let's say that I create a very nice like hello world.html, but like when I curl my Nginx like container, I only see like a default page like from the 90s. And in order to like customize your Nginx page, you would do something like docker run -v and map like the path of your custom HTML file into like the Nginx container and like default HTML page. So essentially, when you do the command that I show here, you are leveraging the mount namespace isolation because the container sees like its own view of the file system, kind of like isolated from the host. In order to like expose the files from the host to the container, you have to do something like this. Last but not least, we would look into cgroup. So for example, like we are trying to like we start serving traffic to this Nginx container, right? We get a lot of traffic. We probably don't want to like overload the machine, making the machine blowing up because of like the Nginx process eats all the resources. So this is where you probably want to leverage cgroup, which is a kernel feature to allocate and limit resources, right? In this example, I'm trying to limit the memory and the CPU usage of the container. Okay, so to sum up from the examples we just looked at, there are 7 pillars of Linux namespaces. The first one is the PID namespace, which target like the process IDs. What this means for the container is that each container will has its own view of the process tree, and like the process inside the container would completely blind to the host processes. It thinks that it is its own thing. And the second one would be the network namespace. So each container will kind of have its own like network stack, its own like pod space, routing table, etc. And the next one will be the mount namespace. So each container will have its own view of the file system. Essentially, it will not like have the things that on the host unless you explicitly set that up. And the next one would be cgroup for resource limit. And the last one, which is probably like the most interesting one, we have the user namespace, which target the UID and the group IDs. What does it mean for containers? This namespace gonna do the UID and GID remapping. So for example, the UID 0 inside container, it doesn't necessarily the same, it's not necessarily like the same UID 0 to the outside of the container. And this will be like, a very, very important primitive that we're gonna leverage in the later stage. And besides that, we have the UTS namespace and the IPC namespace. I also want to take a quick step back to look at the whole ecosystem of OCI container, or Docker container, if we say that, because of a lot of this we're gonna mention in later stage. I just want to go over really quick. So on the lowest level, we have the Linux kernel, right? We have the Linux namespace, C groups, seccomps, capabilities of processes, and above one level, we have the low level runtime, things like runc or crun from Red Hat. These are the binaries that actually interface with the kernel to create namespaces, set up C group, and exec the processes. And above that, we have the container engine, things like Docker, Podman, COI, right? Those are the higher level API to manage container lifecycle, interacting with the registry. And one more layer above, we have orchestration layer. You would leverage this, things like Kubernetes, Docker Swarm, when you want to run containers on a large scale, in a distributed manner, right? So this tool helps you to manage the life cycle, scaling up containers, and helping you to set up the connectivity of the containers across the nodes. And this is it for kind of the intro into containers. I would yield the floor to my colleague.
Thank you. Is it working? All right, sweet. Cool. So as Phong mentioned, we kind of covered the basic namespaces and C groups required to create containers. But we wanted to focus on the user namespace specifically because it enables a different type of container. User namespaces themselves, as Phong already mentioned, pretty much just remap UIDs and GIDs, which sounds boring until you think about the implications. What it really enables you to do is map UID 0 in a lower namespace root to just some higher order UID on the host, or in our case, when we're nesting these containers, what we just call the parent namespace. It's not always the host. The way the UID mapping works comes down to two files, really, etc subuid and etc subgid. And the files are very simple. On the left side, you have a Unix name. That's not like shopper, that's shopper, that's me. And it basically says shopper can take UID in this namespace, which is probably the host, but when you're nesting, these can be the parent namespace. 100,000, and then 65K extra UIDs from that range. And it works the same for groups. The reason we give each user something like 65,000 is because we want to allow that user, when they create a user namespace, to SU to whatever set of users are mapped down there. And as we run nested containers, something as simple as running the Ubuntu container off the shelf will have an Ubuntu user in it that's probably UID 1000. So they already need 1000 UIDs just to start the container. And depending on whatever is in that container, we don't know what the etc password file is inside there. So 65K is just kind of a number we start with to start giving out UIDs. Where it gets really interesting, beyond just creating the user namespace, is that when you create a user namespace, you actually become root in that user namespace. So we have the mapping set up as mentioned in the previous slides, but you also gain capsysadmin. And if you have capsysadmin, you have the ability to then further create other namespaces. So all the namespaces Phong was walking us through in the intro, network, mount, PID, etc., you have the ability to do that inside of that user namespace. And it's really powerful because you don't have to be a privileged user to create a user namespace. This is going to show up later in like our multi-tenant environments where we have many users and none of them have root, but we want to give them the access to create user namespaces and thus other namespaces within there. So I was kind of alluding to the fact that we were going to start nesting these. But in order to sort of explain the trade-offs and how to do that, we sort of have this matrix we want to walk you through because it's going to start getting complex really fast. So we call this like our rootful rootless matrix. And we'll kind of go through what we consider the most dangerous way of running Docker to the most secure. On the top left in red, we have probably what, if you run Docker, you're doing when you're not thinking about it. You might have like the Docker daemon running. It's probably running as root. And you just Docker run, pull something off the shelf, and you don't pass a flag that like overrides who the user is. In that case, we call that rootful, which means like the Docker daemon is running as root, and you're probably root inside the container. And since you're root inside that container, if anything goes wrong, you're also root on the host. This is kind of like where we started with Docker, but like over time, as new capabilities sort of emerged, like better practices kind of fell out of that. Scenario B is the same, except when you start the container, maybe you don't start that container as root. So at least that process running in that container is not going to be root. But you know, if a privilege escalation happens in that container and you can become root, you can effectively have the same privileges as root on the host if you get out of that container. The next column, C and D, are where things get considerably more secure and also like enable a lot more creative use cases, especially when it comes to nesting. So in scenario C, we have the Docker daemon, which is not running as root. So this is what they call like rootless mode, where the Docker daemon itself is running as an unprivileged user, and the containers that are started from it are all considered rootless containers. They all heavily, like, you have to use user namespaces to create those containers, but you can still be root inside that container. It's just what we call user namespace root. And that's nice because if anything goes wrong and you do escape the container, you don't actually have access to root on the host. And then scenario D is like the most mature version of this. If you're going to run an application and you kind of know like complete principle of least privilege, what it's going to do, what it will always need to do, the best way to do this is you run the Docker daemon unprivileged, and then you make sure that the container you're running is also running as an unprivileged user. In our case, we mostly stick to scenario C because the things we're doing inside of containers are highly interactive and even user-facing. But scenario D is better for like, you know, your stateless web app where you're just running one process inside of a container and there's no need for anyone to be root, whether that's user namespaced or not. Yeah, kind of alluded to this. Like, why are we even getting into this? Why are we taking on all of this complexity? Why are we going through sort of the headache of figuring out, like, are we a user namespace root or not? We kind of have two standout major areas of focus, which is we want to better support researchers in our multi-tenant HPC environments where things like research and AI training happen. And we also want something to sandbox agents, either in those environments or not. And in the next slides, we'll kind of go through both and how they intersect. So here's some case studies. There's a lot of headache we learned along the way, and we kind of tried to distill it here, something you could take with you without having to go through it yourself. Just as a precursor, when we talk about research clusters, we're usually talking about Slurm clusters. You don't have to know what Slurm is. Just think of it as it's a scheduler that allows users to isolate and share resources in like a cluster environment. It's like heavily common within academia, but we use it too, and we run it on top of containers. The thing we'll focus on the most is what's in pink, which is the login environment. And that's sort of those very interactive and like user-facing containers I was talking about earlier. Here's a zoomed-in view of what we call a login pod. And as I just mentioned, like the login pod is the interactive environment. It's basically a dev server for like a researcher. And we chose to completely containerize the research clusters using Kubernetes as platform engineers. Like to us, there was value in putting everything on top of Kubernetes, making everything a container. Things became portable, predictable, and things like that. But what happened was we sort of like made the abstraction so transparent to the users that they also wanted to run containers. So if we kind of like go through the nesting of what's happening here, we have like a node in green, and that's a Kubernetes node. And then on the node, we have a pod, and the pod is a personalized environment per user. So like each username has their own pod, and in that pod, we have a few containers, and that's what you see in blue. The main container that like researchers and users interact with is called the SSHD container, which, as no surprise, is running SSHD, and that's the thing that they actually interact with. There's a few other containers in blue. In Kubernetes, it's common to run multiple containers in a pod. They share certain namespaces and can communicate. And for a while, it was just the blue box, or the blue boxes. But then they wanted to run containers themselves, because isn't it nice to just pull Redis off the shelf and run it without having to think about what RPM to install or Ubuntu package or building things from source? Yes, it is. So we got to work figuring out how, and that's what we have in yellow. So those boxes in yellow are user namespace containers. One thing to call out here is that in a research cluster, NFS is ubiquitous, and the whole like idea is that as you SSH into this cluster, you kind of have access to a supercomputer, and like any node you jump to, you have the same access to the file system. You're the same user and things like that. So it's kind of like this illusion of one big computer, and the reason that comes up is because the NFS being everywhere has significant consequences when you're nesting user namespaces. And with that, we'll get into the first case study we have, which is that etc sub-UID file we mentioned earlier that maps users to ranges of subordinate UIDs. Doesn't mean a lot when you have NFS in the picture. And the reason is NFS is not user namespace aware. So what that means for us is if each individual login pod has an etc sub-UID file, we have to make sure that the UIDs we allocate to each user do not overlap in any way. Because if we do, it basically means they can start a container, SU to a common user, write to NFS, and we won't really have a trail of who did what. Fortunately, we caught this as we were testing rolling out nested containers. But this would have been quite a headache for us to figure out down the road. There are other options in NFS to get around this. Things like Kerberos seem to come up in discussions. For us, taking on the complexity of Kerberos wasn't worth it. So instead, we just came up with a UID mapping scheme where we just multiplied the user's UID by how many UIDs we want to give them, sort of map them into this int32 wide namespace, and now we're good. So we know for every set of 65,000 UIDs who could have done what on NFS at that point in time. For us, that's better than Kerberos. If you have experience with this in Kerberos, I'm interested to know. As mentioned, this is the fix. We have disjoint sub-UID ranges. So instead of what you see on the left, where like Alice and Bob might be allocated into either the identical range or an overlapping range. We just have to make sure that they never overlap, and then things are fine. Another use case we had for running a nested container in that login pod was jailing the agents. So we started with Claude Code, but it's the same for all of them, whether it's like Gemini or Codex or whatever. The idea is like these agents are super powerful. They have access to the internet. They have access to your code base. And they might have access to sensitive data. And having access to all three at the same time is sort of a recipe for a disaster because of things like prompt injection attacks. Yeah. So we don't want to allow these agents to have access to all three of those like major areas of concern. So we came up with a way to shove the agents into a nested container and tried to limit its access to 2 of 3 of those. The way we did it is we have Podman running inside of the login pod, and really what happens is when the user like invokes the agent, let's say it's Claude, it actually invokes a wrapper script of ours that will invoke Podman, which will create a Claude container. And before that container boots, we went through in the previous slides how once the user namespace is created, a network namespace is created, we actually just run an IP tables rule that says, absolutely no traffic can leave from this network namespace except through, let's say, port 443 on this specific IP. That IP happens to be the inference endpoint for the agent, so that the agent itself can talk to the inference server, but cannot talk to the internet to go fetch arbitrary data or anything like that. At the same time, we have a mount namespace, so we can bind mount in the user's home directory and things like that from NFS. And yeah, at that point, Claude can then start. It could even start as root. We don't do that, but it's user namespace root, so it's probably not a good idea, but it's not the end of the world either. And we have Slurp for NetNS, which handles all the user namespace and rootless networking that we set the IP tables rules to. So if you don't know what Slurp for NetNS is, it's basically a project that allows you to set up network devices and like vETH pairs and things like that. At least it presents the illusion that that's what you're doing without needing root access. So since all of our users in these clusters are just themselves, they never have root, whether that's user namespace or not, at least at the pod layer. Slurp for NetNS lets us set up the network the way we want. The last case study we have inside of the login pods is not only do users want to pull containers off the shelf with Podman or run the agent via Podman indirectly, once they have Podman, the expectation is they can use Podman to build containers as well. So like in testing, we had very simple Docker files that just did from X, copy Y to Y, and okay, the container's built, and we thought we were done. Well, very quickly after, we tried to run a more complex build. Pretty much any build with a run instruction will fail with this error: mount proc to proc operation not permitted. And it was kind of a devastating wall to hit, because if you think about all the permissions you're supposed to have, you're like, hey, I'm a user in a user namespace, and I'm root, and I have capsysadmin. Why can't I create a new PID namespace and allow proc to mount to proc? And the reason is not obvious, but it's because the kernel says you can't. Again, we're running inside of a pod in Kubernetes, which means we're started by the kubelet. And the kubelet is very opinionated. And it says, oh, I see you're starting a container. Let me helpfully bind mount a bunch of junk over proc for you, just in case you ever become root and try to do something dangerous. And that's good as long as you're not nesting containers, which we are. So we have a different problem, which is we need a way to have proc that isn't masked. So after many like long nights trying to figure out what to do. We randomly tried bind mounting /proc to just a random path, which we've called pure proc. And the trick here is to make sure you don't do it recursively. As soon as you do that, all of a sudden, like, you can create PID namespaces and your run instructions will work. We don't know why, we didn't know why that worked for probably a year, but it went to production because it worked. After some time, we did figure out what was happening. Basically, the kernel has this functionality called mount to revealing. And what it's checking is this mount, like from procfs, going to be too revealing? And you want the answer to be yes, but usually it's no if you're inside of a pod, because the kubelet has helpfully bind mounted a bunch of junk over proc for you. So by nature of creating this bind mount to literally anything, that function will then say, you know what, you would have been able to figure it out anyways because you didn't recursively bind mount all the junk with you. So now you can create that PID namespace. And things that seem like they should work actually began working. That's it from within the login pod, and I'm going to pass it back to Phong to talk about some other cases that are not in the HPC clusters.
Thanks, John, for sharing about the HPC use case. Those were definitely crazy. I guarantee this one will be less crazy. So we have seen, like, how we do like container in container for HPC use cases, and now we have a different one for non-HPC, which will be building containers at large scale. So the case study here is that at Meta, specifically my team, we have a centralized container build platform, a shared service for internal team to build OCI container images without managing their own build infrastructure. Our customers just have to define 3 things to us. The first one would be the build config. Tell us what are the internal packages that you need, what are the dependencies that you need, how much like resource that you need, like how much disk, how much memory, and what is the target architecture. We support x86 and ARM. And the second one would be the Dockerify, which is like, the recipe for a Docker container, right? This is like pretty obvious. And the last one would be how to trigger your build. There are 2 ways. We have the internal COI for ad hoc builds, and we have the CI/CD system for automated production build. For this slide, I would walk you through kind of like the high level architecture of this build system. So TLDR, it starts from a local build contact assembly to a remote execution build happening on AWS EKS. So let's start from the left side. So inside Meta internal, the developer would trigger a build job via the CLI or the automation. The container build system would assemble the build context, pulling the build inputs from our internal VCS and from different artifact resources, for example, our blob storage and then internal RPMs. And then it will kind of like, bundle everything into a table and would ship that table to S3. And then on AWS, we have an EKS build cluster. The build system would start a Kubernetes pod on that EKS cluster, and that inside that EKS pod, the pod would pull the build context from S3, execute the build, and publish the output artifact to our container registry, which is hosted on AWS ECR. And the special thing about this this Kubernetes pod is that it runs something called BuildKit, which is an open source tool for building OCI containers on Kubernetes. And a bit of history lesson here. Before BuildKit, we were using a different tool. It was called Kaneko. It served us very well, but we were hitting the ceiling. So the Kaneko GitHub repo was archived last summer, back in June 2025. So no more patches. We needed a tool that could keep up with our scale and the requirements. And BuildKit was like, the best choice for two main reasons. First of all, it would be the speed. BuildKit allows parallel execution, right? BuildKit would transform a Dockerfile into a graph and stop it concurrently, while Kaneka would like go through like every step inside the Dockerfile sequentially, which is pretty inefficient. And BuildKit leverage like native kernel overlay MS so that it can detect like instant file system change instead of Kaneka, which would like kind of like brute force the file system walking through like the file system after like every run command. And the second aspect here is security. BuildKit offers more like deployment model. It offers like rootful user namespace and rootless mode, while Kaneka only offers rootful mode, which is not that great. And this will be like a very important part that I will jump onto later on. And also like another thing is BuildKit enforce stricter Dockerfile semantics. So, okay, we have mentioned BuildKit, the build system. Where's the nested container here? So, BuildKit is actually where this nested container model happens. So, like I mentioned, we run BuildKit inside a Kubernetes pod, right, which is a container. And inside the BuildKit container, it has a process called the process of the BuildKit daemon, which essentially will create nested sandbox, a new user namespace for every run instruction in the Dockerfile. So essentially, every time you do the Docker, like you build a Dockerfile, right? You embrace like a run command, like that run command will get executed inside the user namespace, which offer an extra layer of isolation. And BuildKit leverage runC, which is like the lower level container runtime, to create this sandbox on the fly. And yeah, and like I mentioned, there are different like security models for deploying BuildKit, rootful, rootless, and user namespace. And we pick user namespace BuildKit for multiple reasons. So to use this model, we set on our Kubernetes pod spec host user equals false and privilege to true, and host users to false essentially would run your pod in user namespace mode. And we have this diagram kind of like break down what happens. So when you start the pod, containerd would create the namespace, which is user namespace like 1, 2, 3, like the yellow box here. And then it will create the pod, the BuildKit pod. And inside the pod, we have a BuildKit daemon process running. Inside the pod, the UID for that BuildKit process would be 0. But actually, it's just a fake root because we are running the container inside the user namespace. It gets mapped to the host. So on the host, like the actual UID of that process will be a non-root UID. For example, UID 100,000, something like that, right? And then when the BuildKit daemon execute a Dockerfile, it runs some commands, right? So every time it bumps into a run instruction, it will create a user namespace, and the run instruction, it will create a user namespace, like you see user namespace 4, 5, 6, right? And then every time there's a run command, the run command will get executed inside that little user namespace. So even though the run command, UID inside the user namespace is 0, it is actually a non-root UID to the pod, to the BuildKit pod. And then it still have another layer of mapping to the actual host. So there's 2 layers of isolation here, which is pretty great. Yeah, so before ending this section, I would love to walk you through some challenges that we hit along the way. So the first part is that when we were evaluating this solution, we also look at rootless BuildKit because of rootless is kind of the dream, but it was too tricky, I would say. We look at the rootless BuildKit, rootless on the pod level, doing things like run the pod as a non-root user. We look at this, but however, it requires disabling the process sandbox. So essentially, what it means is that you would run the BuildKit daemon on the same user namespace with whatever run command that you would execute. So technically, if you get like a malicious Dockerfile, like that command from the commands from that malicious Dockerfile can break the Docker, like can break the build kit daemon and like do bad things, which is not that great. And another kind of like another model we could think about, it's like the rootless end-to-end, right? Maybe like run everything rootless from like the kubelet level all the way inside. This is kind of like very very like this is kind of like, I guess this is like the dream world, right? But however, this would require a lot of like node level runtime config and Kubernetes feature flag changes. Unfortunately, we are using managed Kubernetes distribution, EKS in this case, which is not that easy to do that. I know that EKS doesn't allow people to use like alpha or beta feature. I think they only allow GA under certain requirements as well. So yeah, this led us to pick like the user namespace model. And the second one would be the Dockerfile compatibility. So when we were with Kaneko, everything was rootful. So you were root, technically you could do anything you want. Not too much like limit for you, but when we moved to like user namespace model, things would change. Like you will no longer allowed to do like operations on privileged file system like proc or sys, and like we have seen cases of people doing like a very like open grep or like a phi command in the Dockerfile that touching like the proc or the sys and the sys file system, which will not work when we move to BuildKit. The solution would be, we kind of have the feature gate for people so they can switch, they can like decide whether they want to move to the new BuildKit model or they stay with Kaneko and do like the rest of the migration in the meantime. So yeah, this should be this last slide in our presentation. And thanks everyone for listening. I know it was a lot of content, and thanks all the SCaLE organizer. Thanks Meta and AI for making this presentation happen. Yep.
Do you have any data you could share on what were the performance gains that you saw from switching to BuildKit from Kaneko?
Yeah, we did some benchmarking internally. Like, I would say like we have seen some cases like, for example, like we mostly focus on like the kind of like the build time kind of like thing. So we have some giant container which would take like an hour when you use like vanilla Kaneko, right? No tuning. I know there are some tunings with Kaneko, but then when we move to like vanilla BuildKit, it would be down to like 20 minutes, which is great. I think most of the bottleneck is like how it deals with like the file system, because like Kaneko kind of like traverse like the whole file system checking for like the changes, and that part is pretty inefficient. Yeah.
Yeah,
could you talk a little bit more about how you provision NFS within your cluster, you make it available everywhere?
Yeah. So is this, yeah. It's simpler, like running NFS is a pain no matter what, but it's really just NFS for us. The biggest like trick we have for doing it within Kubernetes is we have basically a little cron job on every node that is constantly looking for new exports and mounting them. And then we bind mount like the highest parent into the pod so that the pod never needs to restart. So as the exports come and go, as long as that parent mount was bind mounted in when the pod started, we get a lot of flexibility that way. But as far as how we provision, another cron job somewhere else is just basically reading a config file saying, hey, there's a new export for me to make, needs to be this size on this shard and things like that. But it's pretty vanilla NFS for us. Anything else? It's both. So in some cases, it's 4 fronting v3, but most of the time it's v3.
This might have been answered by the previous question, but one of the things I run into with like running a scalable like build system is like managing the Docker build cache. So is that handled by the NFS layer?
In our case, so we had caching with Conoco, and it's already faster with BuildKit to not even have caching. So we haven't put a lot of investment in it yet, but in that build cluster, we don't have NFS. I think Fong has ideas for how we're going to do caching, though.
So like in terms of like like in our build system, we actually like that like there are some manifests, right? We actually like do some manual stuff with like the manifest. So in order like we were using like Docker V2 manifest or something with Kaneko, it was happy with it. But I think when you move to like BuildKit, I think you have to move to like OCI manifest, something like that. There are some changes there. I'm still like like that's like kind of like the plan for like next chap to like look into it and maybe do the migration so that like the caching would work end to end. But overall, like BuildKit is already like pretty efficient. So like yeah.
Any more? Oh, yep, more.
So is your system like engineered for arbitrary levels of nestiness? And secondly, do these researchers that you described as end users of the system like use arbitrary levels of nestedness?
No, it gets really complex really fast, so they just go one layer deeper most of the time. But I have done it as a concept. It will work. I've run Podman and Podman via the Podman container in the login pod just to make sure everything worked, and it did. So.
Do your security concepts get like repeated by doing that?
Yes.
So that nesting levels are secure automatically?
Yes, but it gets so complex it's like impossible to figure out what's going wrong. So, yeah, like it's basically just like the pod is started rootful by the kubelet, and then the users are never root. And then from then on, it's all user namespaces down. So if you have the stomach for the complexity, you can make it work, but you're never getting real root anywhere. Like that boundary never gets crossed. Yep.
How many inner containers do you have inside one outer container?
How many containers in what?
How many inner containers do you have inside one outer container?
Not many, but it's also up to the user. So since every login pod is like a personal dev server, they can start, I mean, as long as they don't fill their tempfs, 10s, 20s, it's really up to them depending on like what compose file they ran that like started those containers. Yeah.
You probably have time for one more if there's a... All right. Thank you very much.
Cool. Thank you.
turn it on, flip, wait 2 seconds, and then you'll have audio. Flip up on this guy, and then wait a couple seconds. And you're all set.
Hello, hello, hello. Can you hear me? Can you hear me? Okay, good. Let me get started. Um, I'm Tony from LinkedIn. I'm Tony from LinkedIn.
Directly in front of it.
Okay. How about now? How about now? Is it good? Okay. Okay. Okay, hello everyone. Thank you for coming to my talk. I'm Tony. I work at LinkedIn and working on analytical databases. And I like anything in between databases, distributed systems, and yeah, so on. So today's topic is zero downtime case migration of our 14K Apache Pinot nodes at LinkedIn. So how many of you have heard of OLAP? How about Pinot? How many of you have heard of Pinot? Okay, 2 people. That's great. Uh, I'm going to start with what Apache Pinot is and how we use it at LinkedIn. And there are 2 prerequisites that we implemented before we start migrating. So those 2 are the availability zone aware shard placement, also known as AZ aware shard placement, and containerization. So to run application on container, you have to containerize first. So there's a second prereq. And then I'm going to dive into the migration work orchestrator itself. To eliminate the human toil entirely, we designed and implemented a migration orchestrator, built-in temporal. So I will go over the design and the implementation last. Okay, let's start. What is Pinot? Pinot is a real-time distributed OLAP data store. It's built for low latency and high throughput analytics. So how we use it at LinkedIn? First, you might have used it or at least know about it a little if you have used LinkedIn before, which is the member-facing and enterprise use cases. Probably the most well-known example is who view my profile. It says who's view your profile, but same thing. So when someone checks your profile, it shows you how many people check your profile last 90 days, 30 days, 7 days. You can filter differently, but this is powered by Pinot. Another use case internally at LinkedIn is the internal products in BI. This example is we use Pinot to basically check our growth for the last 1 year or 2 years. So these 2 main use cases are how we primarily use at LinkedIn. We don't have to know all about the Pinot architecture, but I'm going to go over really surface level at least. So let's start from the top. When people query Pinot, they query broker. It is the routing layer, so this is the reading path starts. And we go down, and there are 2 separate paths for write. The one on the left is the real time. It's what we call real time. You can think of Kafka or Kinesis. There are other flavors of this. But when you want the real-time update in Pinot, this is how you insert data. I guess this is how we ingest data from real time. Another write path is the offline path. It's from the right. It's from the offline sources. And there's some kind of offline job you can use to ingest Pinot into the offline servers. So we have 2 different types of servers depending on the use case. For real-time path, we use real-time servers. For offline, use the offline servers. You can pick and choose which one fits your use case. And this green box here is Zookeeper, which we use for metadata storage, which is connected by our controller, which also does other admin API as well. So I'm going to talk a little bit about the scale of Pinot at LinkedIn. There are roughly 300K QPS and 10,000 serving hosts, including real-time and offline. And there are 2,000 broker/routing hosts. And we have, I think, currently over 5,000 Pinot tables. This is slightly outdated. So this is the scale we operate at LinkedIn for Pinot. So the question is, how can I migrate 14 stateful hosts? And a very reasonable person may say, can you just turn off LinkedIn for 2 weeks? And it's easy. You just turn off, so the hosts are not used. You can migrate, and everything's great. The real challenge here is we can't do that. So how can I migrate 14 stateful hosts with no downtime? That's important. And we also want no query latency impact. Before I reveal the secret of how you do it, I'm going to go over a little database 101 in case you are not familiar with databases or you're new to tech. So I'm going to start us with shards and replicas. Think about this table. I just named these students. It can be anything. And there are a lot of data. There are 80 terabytes of data for the students table. And it has data from grade 1 to 6. The problem with this is it's kind of hard to operate when you just have one big table. It can go down anytime and you just lose access to your data table. So one technique is known sharding. It's kind of how you divide data. Instead of having one big students table from grade 1 to 6, one strategy you can think of is, how about just have a different shard per grade? So you have grade 1, 2, 3, 4, 5, 6 in a separate shards. Each shard has a different data. So grade 1 has 13 terabytes of data, and grade 3 has 16 terabytes of data. This is kind of natural because sometimes, data is different based on the actual characteristic of the data itself. So in this case, they're slightly different, but now you achieve this separation. Then what is replicas? Replication is something you do for if you want high availability. So instead of having one copy, the primary database on the left, you can just have the exact same copy, and you can have another exact same copy. So in my example, there are 3 exact same data replicated across, replicated across 3. So there's grade 1, and there's also grade 1, there's also grade 1. These 3 are the same exact data, holding the same exact rows. The only difference is now you can scale. So instead of going queries to this one single table, you can go to the copy table 1, or you can go to the copy table 2. So you achieve 2 distinct goals with replicas and sharding. Now, if one go down, let's say copy 1 is down because the underlying host has issues, it can still go to copy 0, which is the primary table, or it can go to copy 2. At the same time, you can serve more customers because now you have, let's say, 3 distinct hosts serving more queries than before. So you have essentially have more capacity. Okay, with that in mind, I'll go to the first prerequisite, which is availability zone aware shard placement. Have you guys heard of AZs, also known as availability zones? It's pretty common concept in public cloud as well. This example, I just use a random data center in California, and there are 4 different zones. Each zone is physically isolated. They have their own power. They have their own networking infra. So in theory, one zone's outage should not impact other zones. So if zone A goes down, it should not impact zone B, zone C, or zone D. Okay, simple enough. So the question as a user who put data into the data centers and AZs, it's how to put shards into these different zones. Can you just put like this is the one strategy you can think of. I'm just going to put grade 1 in zone A, grade 2 in zone B, grade 3 in zone C, and so on. So there are 4 grades with 2 replicas each. But another way you can think of is you can kind of distribute so that in zone A, we have grade 1 and 2. Zone B has 2 and 1. And C, 3 and 4, 4 and 3. So the advantage of the right side, the placement of the right side is if one zone goes down, you still have one up replica. So zone A goes down, can you query grade 1? Yeah, you can just go to zone B. Same for grade 2. You can just go to zone B. There may be slight latency impact, but at least it's not fully down. But for the first case, if zone A goes down, you cannot query grade A at all. So this is important when you are placing shards into AZs. The only problem is for bigger table, we have 10 K shards, 40 replicas, and 10 AZs plus. So the problem is a lot more complex than the toy example I just showed you. And this is just one table. We have 5,000 tables at LinkedIn. There are kind of 3 variables we can control. One is AZ, the other one is hosts, and the last one is shards. And you can think of there are 2 distinct knobs. One is how to put shards into hosts. The other one is how to put hosts in AZs. Let me start with the first problem, how to put shards in hosts. I just used 12 hosts as an example, and we have grade 1 to grade 8. The strategy we are using at LinkedIn is we just group 4 hosts into one group. So we have group 0, group 1, and group 2. And this is how you think about groups. One group serves all grades. So group 0 serve grade 1 to 8. Sorry, replica group 0 serve group 1, grade 1 to 8. Same for replica group 1, they serve grade 1 to 8. The exact placement of shard into host can be different, but at least one group serve all grades. So replica group 0, hey, I serve all grades. Replica group 1, hey, I serve all grades. And same for the replica group 2. So this is replica group, and the only problem there is it's not predictable. So here server A has 3 shards, server F has 3 shards, but server G has 1 shard. We want to store shards predictably into hosts. The strategy we came up with is think of it as an array. This Python, Java, doesn't matter. Within a group, we start with index 0, 2, 1, 2, and 3, because there are 4 servers per group. And within a index, all servers serve the same shards. So index 0, the pink mirror server set, what you call it. We all have the same shards. We all have the same data. Index 1, server B, F, and J, they have the same data. Same story for index 2 and 3. So if I actually put shards into this mirror server sets, it looks like this now. So mirror server set, index 0, now has grade 1 and 8. And horizontally, they all have the same shards. This is what I meant by mirror. It's kind of mirror each other. Same for the red mirror server set, index 1, and the purple and blue. Now we can put shards into hosts predictably. This was the point of mirror server set. That was actually just the first knob. Second knob is how to put hosts into these AZs. We keep the same mirror server set strategy, but the only additional constraint is the AZ. Within a mirror server set, within, let's say, pink mirror server set, there should be no overlapping AZs for safety. So here, I just put it 0, 1, 2, no overlap. Same for the red mirror server set, 0, 1, 2, there's no overlap. Why do you want to do this? It's similar to the toy example I showed you. Let's say AZ1 goes down. Are we losing any data, or is there any data not queryable? Not really. With this strategy, even though one AZ is fully down, the data is still available in other servers. So for the first row, pink mirror server set, server A is down, but query can still be served by server E or server I. This is why we combine the AZ diversity with mirror server set. Oh, by the way, this is not tied to one table. So far, the example was the students table, but it can apply to multiple tables. So student table, courses table, staff table, they're all served by the same replica groups. And if one go down, it's still safe because there are other copies available in other AZs. Yeah, so this is why with AZ diversity and mirror server sets, one AZ going fully down is safe for all tables served by a cluster. Second prerequisite, to run a containerized application, we need to containerize. There are multiple SKUs at Pinot, internally in LinkedIn, so this is how we manage it. So there are more than 4 types. These are the 4 main types. We use the Kubernetes label. So for the first example is Pinot server, 64 gigabytes of memory, and SSD. When there's no SSD size, we assume it's 3.2, which is the standard SSD size at LinkedIn for Pinot team. And look at this example, the blue boxes. Now the memory size is 128, but it has a lot bigger disk. It has 6.4 terabytes SSD. So we label them differently, these two as well. And we use node affinity. So depending on the workload requirement, we can just use a different SKU. And if their characteristics change, we migrate to a different SKU type. Also using the node affinity. And before migration, Pinot team at LinkedIn used to have a bunch of puppet models to do different things. We had a kernel setting. This case for the mmap, we had a max map count. We also had the SSD mounting logic, NFS mounting logic, Nginx configuration. There are probably more. In this new world, before migration, we eliminate the needs for a lot of kernel-specific settings. For instance, we introduced M-advice feature in the OSS Pinot code. We use the persistent volume for SSD mounting and NFS mounting. And for Nginx, we moved to an embedded, we embedded into the container image itself. I want to get back to the architecture a little, because it will help us to find the correct migration strategy. Remember, there are 4 main components. We have broker, server, real-time, server, offline, and we have controller, which kind of controls the whole cluster. But not all of them are stateful, I'll say. Broker, which is the routing layer, it's pretty much stateless. They accept queries, yes, and there are routing layer, but they don't have any data on disk. Controller as well, they are also Helix controller. They're managing other Pinot components, so broker, server, they're all managed by controller. They also have some admin API to rebalance or create a table, delete a table, but they do not persist any data on disk. So they're also kind of stateless. Real-time server, they host shards and they serve queries. They do persist data on disk, and same story for offline servers. So broker and controller, they are stateless applications. So we can use a migration strategy that fits stateless application. For real-time server and offline server, they are stateful. They have data on their disk. So we use the stateful application. Strategy for migration. One thing I haven't mentioned, but very important, is host maintenance or any kind of maintenance. This it's new for the Kubernetes world, for us at least. Kubernetes is aware of the pod health and the host health. One thing they are not aware of, at least for our use case, is the partitions, the shards. How the shards placed into hosts is something Kubernetes is not aware of. So we built some, my colleagues built ACM, I think it's called Application Cluster Manager. So what they do is for deployment, uplift, host, swaps, all these different applications, someone will ask ACM, hey, I want to stop server A and B. They're unhealthy, or we found a hardware issue. I want to stop. So ACM talked to the host shard states in Zookeeper. So you kind of check, are there enough replicas up? If there are only one replica up, if you take this down, there's no more replica, and core is gonna fail. It also verified the enough replicas up before stopping server A/B. Second step was checking all the states. Third step is verify if there are enough up. And after checking step 2 and 3, ACM is like, we can stop server B, but you cannot stop server A because there are not many replicas are up. This is the role of ACM. There's actually another talk by my colleague at a KubeCon. You can check their, I linked in the slide, so you can check their talk later on. Okay, so we covered 2 prerequisites before we starting migration itself. And how did we actually migrate? We used the migration orchestrator, which is kind of a, because we have 5,000 tables, and I'm sure I'll make mistakes if I have to migrate 5,000 tables manually. So this orchestrator is built in temporal, and it's fully automated. And then it's designed to like continuously retry if there's any failure in the process. So I mentioned migration strategies a couple times when I talk about stateful versus stateless. This is what I meant by the strategies. You can either do in place or out of place. What are the differences? For in place, you take down one host. I use server A as an example, and use the same exact host in Kate's stateful set. So the data is not moved. You have the same exact disk. So you don't have to move data with the in-place migration. For out-of-place migration, you just throw a bunch of servers in Kate's. So my Kate's deployment has 4 new servers, server E, F, G, and H. And then you just take down the legacy VM hosts. So if there is data in this legacy VM, it's lost. They have to be replicated before they get deleted. There are some pros and cons between these 2 migration strategies. For in place, they don't require spare hardware because they're moving the exact same hosts. And they don't require data movement. It's the same exact data, SSD. But they're slow. You have to do one at a time or a couple at a time. You can't just turn off everything and move. And it's also tricky to handle bad hosts because it's data involved, and you lose the data during the migration if there's a bad host. For out-of-place migration, it's the mirror polar opposite. It's super fast. You move the whole thing at once or in a few steps. And handling bad hosts is easy. Just replace it. It's a new host. But the problem is they require spare hardware. Compared to in-place migration, in out-of-place migration, you needed the same number of hosts in Kubernetes. And they also require data movement if there's any data in the legacy VM. This is why for stateless applications, we decided to use the out-of-place migration strategy. For stateful applications, we use the in-place migration strategy. This is all great, and the question might come up, how do you ensure the safety and performance during migration? Because there may be performance degradation in between. This is where the AZ-aware shard placement from part 2 becomes handy. Now, we know if you take down one whole MZ, it's safe. There's no impact. There's no latency impact. So what we can do is, even for in-place migration, take down the whole MZ. So 1, 2, 3, 4. Take down 4 servers at a time. So you just need 3 iterations for migration to finish. So take down AZ0, make sure they're up, and then take down AZ1, put it up in the Kubernetes, make sure they're up, and then move on to the next AZ. In terms of performance, we build the validation in the orchestrator itself. So for each host migrated, we check, is the host healthy? And we do some log validation. Are there any new errors from this migration? Is the host ingesting data, just like before? Finally, we do the metric validation. Is the query latency in expected range? Is the CPU usage in expected range? And I believe there are a couple more tests we do for each host. Okay. Finally, the meaty part. This is the temporal workflow we built for in-place migration. Let's say you want to migrate the students table. We gather workload requirements for student table. It can be, oh yeah, I want 24 virtual core, 64 gigabytes of memory, and I want 6 replicas. So based on this requirement, we write Helm values, and we commit. There's a separate the manifest apply pipeline. So the next step, we call it temporal activity. It just keeps pulling and wait for the manifest application is done. Once it's done, we trigger the in-place migrator. So this is what it, yeah. So going back to the previous slide, it's pretty much the same thing. It just go AZ by AZ, take down, move it to Kubernetes, make sure they're good, and move on to the next AZ. Oh, there are also some constraints we put on just to be safe. We only migrate during business hours, and we also have other constraints if there are any active incident that's impacting latency or availability, we don't want to migrate. So we had a constraint there as well. And once everything's done, we just add cluster as a deployment target. So for our next deployment, it will be included there. We have a similar temporal workflow for out-of-place migration. That one is a little simpler than this. And the beauty of this orchestrator can migrate many tables concurrently. It doesn't have to do one at a time because they're all served by different clusters. It's safe to be migrated concurrently. So in this example, we migrate this central orchestrator triggers a workflow to migrate students table, but it also triggers workflow for child workflow for staff table and parents table. This is just a screenshot of what we used. The main orchestrator workflow has a lot of child workflows. So it shows 215 child workflows. This means at some point we migrated 215 tables under this workflow. Okay, some lessons learned and the future. It's kind of counterintuitive, but you will save migration time by spending more time prepping. We actually planned and implemented the design for, I think, almost a year, maybe a little less than a year. And that saved a lot of headache during the migration. The mirror server set concept and containerization, we also did a bunch of improvement in the code base itself. So they actually saved the time for the actual migration of 3 different data centers. Oh, you have to be careful of deploying during the migration, because during migration, you temporarily have less replicas. And if you are not careful, you can take down the cluster. Some future, Pinot pod stacking support is not there because of some complication. So this is what we are actively working on, as well as a K8s operator to manage Pinot clusters. So we want to rebalance and uplift, downlift. We want all these things to be done by Pinot K8s operator in the future. Okay, that's it for my talk. Special thanks to my teammates, Dino, Kanja, and my managers who made it happen, Sharda, Sid, and Amar. Thank you.
So in the ACM part that you guys design, it mentions that your infrastructure is separated into different servers that kind of share different charts. But in terms of that, how does it make the decision of I need to shut down server, I can shut down server B, but I cannot shut down server A? Like, what's the decision between why not A or why not B?
Because in terms of shard placement, it could be the case that server A has, I'm going to use the students table example, as let's say grade 2 and server, but there are already deployment going on or some kind of operation going on other hosts serving grade A, sorry, grade 1. So if you take down server A, there's no more copy of grade 1 anywhere. So you cannot stop server A anymore. But server B, maybe all the other replicas are healthy and up. There's no other operation going on. So it's safe to take down server B. So in this case, server A is not safe because of overall replication status. But server B is safe because it also checks other replication status of sharing the same shards.
Thank you.
Are there any other questions? Okay, thank you for attending the talk.
Thank you.
Check, check. Good. Yeah. Hi, all. My name is Srinathan. I'm from a company called ZAS.io, anything as a service input output. And I'm here to present about building an AI factory with pure upstream open source projects. This talk is not about creating a large language model or doing post-training or pre-training. This is purely a talk for building AI infrastructure. And I have 4 points which I will cover today. First, we'll talk about why we think there needs to be an integrated open source AI factory. And we look into the architecture of the AI factory which we are going to present today. And we will look into what's the hardware infrastructure utilized for spinning up this demo. And finally, we will just look into the data flow pipeline of how, from an object storage, we are able to push it into a generative AI or an agentic AI without using any publicly available APIs, right? So first thing, if we look into the evolution of infrastructure platforms, before I begin, I just have one small question to the audience. How many of you guys here use AI in your own infrastructure? Quite a few, great. Good. So one of the things which I've been observing is from 2008 till 2014-15, there was this virtualization era where projects like OpenStack, CloudStack, OpenNebula, Eucalyptus created a framework for cloud computing, based virtualization and infrastructure as a service. Then for the cloud native era, right, Kubernetes came in. Kubernetes set standards for microservices and all the good things. And that continues to be the trend till date. But one thing which we've been observing is in the AI native era, there is no Kubernetes. There is no OpenStack. You just have fragmented tools like Kubeflow, MLflow, Ray, VLM, and many more. But there isn't an integrated orchestrator for AI native workloads. And we strongly believe this AI native orchestrator should be similar like what Kubernetes did for cloud native. There needs to be a new kind of a Kubernetes for AI native workloads. So that's the, at least that's the thought, right? So with that as a thought, we decided, why not we build a reference architecture and build the reference architecture with only upstream projects and glue it together and see what it looks like. And one of the things which I'm very let's say focused on is how is this going to get evolved over a period of time? Because we have to take into consideration Kubernetes kind of platforms were built by consumer web giants or big tech companies like Google, who had tremendous amount of exposure in working in web scale computing. But as an hobbyist, as an startup, mid-sized organization, you do not get the exposure of what the big tech companies get. But fortunately, we've been working on kind of a mid to large scale systems, especially when it comes to cloud native and virtualization services. So that wisdom has made us think, let's try to do something here. And I'm going to just present a reference fabric. I'm not just going to just do a theory here. We as well have deployed a small demonstration, and I hope that demo is going to, as well work well. So to start with, we are having a unified control plane. So this we have built by using by using Cloudscape. Cloudscape happens to be Amazon Web Services user interface. It's Apache 2 license, and we have taken that. And for the core infrastructure, we are using Kubernetes, which is running on top of KVM. KVM itself is orchestrated with OpenNebula. And you'll be surprised why we are using OpenNebula in the next slide. The hardware footprint is very, very minimal, keeping hobbyist in mind. And third thing is, we are not just speaking about an AI serving infrastructure, but we are as well looking into data, because if you don't have data, you don't have proper AI. And especially people who practice private AI knows data is the most critical component to make an AI work. So we are having a data lakehouse based on Apache Iceberg, which runs on top of Chef S3. Then for the AI platform and MLOps, we are using Kubeflow, MLflow, Feast, and we are as well using Langflow and VS Code. Then we have embedding and future pipelines. Then for inference, we are using VLLM, and VLLM is connected to OpenWeb UI. Then for the vector database, we are using Mulvis along with semantic retrieval. You can always use PG vector, that's not a problem. Then we have tried to integrate all of these tools with the key clock single sign-on engine. So you do not have to maintain different credentials for different systems. Rather, you have a single unified SSO binder. And if you're an enterprise, you can connect it to your Active Directory system or your directory services, wherever they are running. And finally, we have an observability system, which is basically based on Grafana and Prometheus. And the whole idea here is, there are point tools, which are great, but we have not seen an integrated stack. And we are just trying to push the data stack and the AI stack and the orchestration and management pane as a single open source AI factory. So that's the idea. Now, that being said, the demo which I'm going to show you in the next few minutes, it's running on just 2 machines, 2 servers. That's it. Obviously, it's not going to give the best results, but this is good enough to understand and build the integrated stack, right? So we are using Hetzner. Again, we are not using any hyperscalers. We are only relying on alternates because there are 2 reasons. I love hyperscalers because learned a lot from them, and they contribute a lot to open source. But at the same time, I'm not able to afford them because the cost at times is very high, and you don't get to own anything after a period of time. It's a subscription. It's like grid. So when it comes to data, when it comes to AI, I think, especially when it's in different parts of the globe, sovereignty matters, ownership matters, right? And in order to embrace those values, we have intentionally looked for systems which do not have anything, which only have the base. And then you're building everything on top of it. So here we have two nodes, just two nodes. One is running in, in a data center in Finland, and other one is running in a data center in Germany. Both are in isolated data centers. Again, because they were cheap, we got it in auction, and we just want to push the limits of software engineering and see where it goes. And so I think we have achieved something. We have 64 vCPUs and 384 GB RAM and 2 TB of SSD at JBOD. This HCI node fundamentally runs a complete Kubernetes workload, and the Kubernetes workload itself is split with KVM cluster, which is orchestrated with OpenNibla. Then we have the fourth node, which is running in Germany, we were forced to take this node because this was the only node available at that cost. So there's no 10 gig here. It's a pure 1 gig WAN bandwidth. And remember, we are in WAN, so anytime anything can go wrong. So henceforth, we block the complete internet, created a secure WireGuard VPN tunnels between both the environments. And this fourth node happens to be one of the Kubernetes worker node to the Kubernetes cluster, a stretched cluster. And we are having it with an RTX 4000 SFF ADA GPU. It has only 20 GB of VRAM, but that's good enough. If you're a developer and hobbyist, you can do a lot with it. And the base operating system is based on Ubuntu, but we can as well use Rocky Linux, Alma, and many other. And the virtualization platform used here is OpenNibla. The reason why we use OpenNibla, it's very lightweight to manage power off VMs. We can obviously use Proxmox as well, or we can even use libvirt without any of this orchestrated, but this is convenient for us. So all of this, end of the day, is powering up Kubeflow service, ML flow service. We are as well running a VLLM service, which does the model serving. We have a Langflow. The vector database is on Mulvus. The AI chat interface is on OpenWeb UI. The data lakehouse is on Iceberg. Container orchestration is on Rancher. We are using Rancher Kubernetes engine. The storage is on Rook Chef. Networking is done with WireGuard. Identity and access management is KeyCloak. The monitoring and observability stack is Grafana. And the only thing we have built here is the unified console, which fundamentally wraps all these different open source projects as a single layer. It has the capability to do orchestration as well. But this platform itself, it's still not fully matured. We are still building it, and we want to release it to the community and have the community drive it further on. So now, this is how the flow is going to look like. If you've been using Ollama kind of tools, when you upload any kind of documents, it fundamentally stores the document in the Ollama memory, right? But the memory itself is not persistent. Now, if you want to, let's say, upload 1 petabyte file storage to a Ollama kind of system, it becomes a little bit challenging. So that's where we believe the current AI factory framework which we built creates a difference. So fundamentally, we have an object storage where you can have n number of documents or content, both structured and unstructured. And there's an ingestion pipeline, and there's an embedding generation created, which then ingests into the vector database. The vector database itself is queried by a VLLM interference engine, and then which is presented with the OpenWeb UI chat interface. And we will look into the live demo of it, what I'm trying to mean here. So now, with this being said, let me go to my demo environment. I have pre-opened many of the windows. just so that I genuinely not trying to stage the demo here. I'm just trying to ensure that this is how it's been working. And unfortunately, because we are running with very little resources, at times the API calls are too slow to respond. So that's why I pre-opened the windows. But nevertheless, we are going to have this code published with Apache 2.0 license, so people can test it out in their own infrastructure and give their comments. So you can see very clearly we have a, so the first thing is this. We have a landing page. And this is completely built on cloud space. And once I click on sign into console, it fundamentally goes to a key clock service. And because key clock is already been authenticated, that's in the cache. And you can see here we have built a similar hamburger menu. And if I click on AI Factory and click on AI Factory dashboard, it provides me all the links to connect to different services like MLflow, LangFlow, RStudio, and so on and so forth. Now, for example, let me click on domains. Let me open the workspace. So you can see here I have, let's say, running instances. Here you can see. So you can see there are different instances running here. There is a VS Code running. There's a Jupyter Lab running, so on and so forth. Now, similarly, if I click on Malvis, you can see there's 2 instances of Malvis database running. So if I click on default, it opens the R2. So everything is integrated here. Similar like how you work in a typical hyperscaler. Now, similar like the Malvis, we have the VLLM. So if I click on VLLM here, we have the complete model which is being used for this VLLM. We can as well see the configuration of it. Then we can as well see the manifest of that VLLM, so on and so forth. Then we have the Open Web UI, which is here, which is opening now. So this gets loaded up. It takes some time, but I have preloaded the Open Web UI here, and I've done some chat with it as well. So let me just show you a few examples of what I'm trying to. Just give me a second. Perfect. So if I show you the connection string of this Open Web UI, if you see the settings, and if I click on connections, you can see we are not using any public APIs. There's no public APIs, right? And all these APIs are connected to internal Kubernetes endpoints and internal Kubernetes ingress. That's it. Now, if I go to my chat, let me try to zoom it back to normal. Just a sec. Perfect. Here we go. Okay. So I was just, having a conversation with the LangGraph engine, which is as well built in here. So let me show you the LangGraph flow which we have built. So this is the LangGraph flow which is being built. So let me try to zoom in here. So there is ingestion workflow and there's a retrieval workflow. So we are fundamentally capturing the data from an object storage, and that is having a PDF reader in it. And then there's a text splitter. And then we are having some embedding generation happening where we are using BGE small model. Then we are injecting that data into Malvis. Now, if I go back to my chat interface, I just put a query towards the LangGraph RAG model, asking it explain AMD GPUs. It's not a generative AI. It doesn't have general intelligence. It's pointed. It's a private AI. It's pointed towards a specific data set. And we intentionally have it in this way. I'll as well show you a generative AI example with the QIN model shortly. So you can see here, the provided context does not contain specific information about AMD GPUs. So it's fundamentally saying the Chef S3 backend, which I'm having, is not having any of AMD documentation. So what I'm going to do is, I have already searched for a certain set of AMD data sheets. So I'm downloading that. I'm putting it in my downloads folder. I'm going to my S3 browser. You can see we have no AMD data sheets here. I'm going to upload a file. I'm going to upload this MI350 GPU. It's uploaded, right? Now, let me go back to my browser. And I'm going to go to the VS Code. This is add to, then, yeah. And I'm just going to run 2 commands. This can be completely automated, but I'm just trying to showcase you the flow. So I'm initiating the ingestion pipeline, right? In real world, this is to be automated, but I'm just showing you the flow. And this ingestion pipeline is the LangGraph, LangFlow pipeline, which I showed you. And you can see right now the ingestion is starting. And because we are running with constrained hardware, the ingestion happens through CPU, not GPU. The interference happens in GPU. We're running just one GPU. Yes, so you can see it's starting now. Let's just wait for a couple of minutes. Now, in the meanwhile, I have Grafana and Prometheus monitoring system, but unfortunately, in the last couple of hours, it's not been working. But I've created a backup for it, where we can see the performance of the GPU through the CLI. And you can very clearly see the GPU memory is almost filled up. We have 20 GB of VRAM, 18 GB is filled up. The GPU power, the GPU cores are still not used. Now let's see what's going to happen once we put the AMD query. So let me go back to my browser. Let me go to VS Code. Here you go. So it has started to execute the job. You can see there's the you can see there's the AMD PDF, and it is as well having a 21 chunks here. So 40% is complete. Probably in next minute or 2, it should get completely done. After, we are going to inject this data into Feast, it's a feature store. Then let's go to the OpenWeb UI and retry the same context which we have given. Here you go. The same set of software with a larger hardware, and we, let's say 25 gig or 40 gig network should give you real-time results. But we are using 1 gig WAN and very limited hardware. So please bear with me. And I suppose most of the people who want to do testing and genuine software development and engineering, we have limited resources, so we need to be a little bit frugal. So here we go. So the ingestion of this thing is done. Now I'm pushing it to the feature store. So Feast is getting applied, and documents are getting updated as Parquet files. Boom. It's done. It's successful. Now, let me go back to my chat. I am going to just regenerate the same query. Now, if I go back to my CLI, you can see the GPU is right now running at 99%. The GPU is fully utilized. So I'm not using any public APIs. That's the message I want to tell. And I promise I'm not doing it. The intention here is what OpenStack did for KVM, Kubernetes did for containers, we intend to do for AI. That's it. Now, something is happening here. You can see GPU's load has gone down, but I am expecting some result. Here you go. Here you go. So previously, it was not able to give us the answer. Now you can see it is able to give the ML350 GPU answer, and it is as well pointed out through which document it is giving the answer. Right? So this is one of the possibilities of building an AI orchestrator. I think it's high time some of the community members gather together and think about how we can build an open source AI orchestrator, an open source AI factory, and virtualization all through the market category was created by VMware. By large, OpenStack had a big say in it. Kubernetes, from day one, has dominated cloud native. I hope someone in open source is able to dominate AI native as well. That's the intent. Yeah. So with that being said, I'm thankful for every one of your time, and thanks for coming here to hear me. And this is mainly possible because of a few engineers who have worked tirelessly and put their additional time beyond their professional time to have this done. Vijay, Dinesh, Vignesh, Vishnuvardhan, Gokul Raj, and Gokula Krishnan, and Vishwa. They have been pivotal in building this stack, and it took us a couple of weeks to get all these things, but we had to burn a little bit more hours to have it done. So that's it. Thank you all. That's it. Yeah.
Thank you. Does anyone have any questions for the speaker?
Yeah. I'm not an AI expert. I'm an orchestration expert.
This is not an AI question.
Okay.
Can you tell us about the auction that got you your servers? The auction? You said
Henster. Henster. It's a German alternate cloud platform.
Okay.
Yeah.
Okay, thanks. Thanks a lot.
Yeah. Because there are many engineers who are specialized in post-training, pre-training. I do not do that. I only do the orchestration of it. So, yeah.
Thank you for the talk. You mentioned that you're planning to open source this under the Apache license. When can we see this code and get access to it?
Our target is to deliver that within the next 90 days. Okay. We want to do it within 90 days, probably within 30 days as well.
Okay.
Yeah.
Thank you.
Anyone else have any questions?
Hi.
Yeah, hi.
Oops. I understand this is a
you're just starting this, but are you already planning on it to be kind of for multi-tenants? So
Yep.
Is that already part of what you folks have created?
Yes. It has to be multi-tenant and as well as a role-based access control, quotas as well. Yeah.
Thank you.
So for folks who already have pieces of this infrastructure, the reference infrastructure that you had today, are you also planning on this being able to be plugged into already existing infrastructure? So we have Ceph, for example. We also have Rancher. We have, a lot of the things that you were talking about. Can we leave our infrastructure as is and put this orchestration layer on top of an already existing infrastructure?
No, that's a great feedback you have given. This is the architecture we need to work on. Because by default, if you take Kubernetes or OpenStack, they are meant for greenfield deployments. Your ask here is, let's say I'm an enterprise, I already have a brownfield. Can you guys integrate with our stack? That means we should have an orchestrate, like a cloud management platform, we should have a API only access. Either you deploy a greenfield or you discover a brownfield. So that's something we can build. I think that's very possible.
Thanks.
Anyone else? Great. Thank you so much for attending the talk, and please give another applause to the speaker.
Yeah, thank you.
I don't know. Check, check. 1, 2, 1, 2. Hey, hey. 1, 2. Check, check. 1, 2, 1, 2. Check, check. Hey, hey. Yeah, no. But no, I think it was him. I honestly think it was just the way he was talking and like the what he was doing. Yeah, you remember him? It was like crackle. We had and we. Oh, okay. Yeah.
Okay, okay, good. Sounds good. Okay, it is 6:15, so I'll go ahead and get started. My name is Justin Fry. I am a senior data engineer working for RX Benefits, and it's randoneering, in case anyone's wondering. Just a quick intro. I'm a forever sysadmin. This is considered, or I've been told, it's sort of like a junk drawer sysadmin. Basically, you have multiple skills in multiple areas and wearing multiple hats. I started my career as a SQL Server DBA, technically a QA engineer, and then eventually moved to SQL Server. I'm actually from the Chicagoland area, but I moved to Boise in 2024, so still Midwest native. And I created a Postgres health check function that I had a talk on previously yesterday. That is an easy to deploy, zero dependency Postgres health check function. So I tried to make this funny as much as I could, mainly because the entire journey that I went through was very comical, at least to me, because at the end of the day, I basically did a full circle. But I thought the best way to describe it was to mirror it off of the 5 stages of grieving. I know that sounds kind of dark, but it's really not. It's supposed to be kind of something funny. So just kind of to go over that denial, this is just another resource to deploy. There's stage 2, anger. Why do I need 3 providers just to initialize a database? 3, bargaining. If I just add 1 more provider, I'll be able to do it. Depression. My module's too complicated and I am the only one that understands it. And acceptance. I'll just build a single-use blank database deployment. So that should be a little bit of foreshadowing, and then, bless you, at the end, there's kind of some quick lessons learned and something very ironic, I guess, when we'll talk about that. So the scenario, I currently work for a healthcare company. So as DevOps was ramping up, they wanted to try and basically restructure the entire CI/CD pipeline. And so they started to work with infrastructure as code. And so for whatever reason, they decided, let's use the database admins to start with infrastructure as code. I feel like that was very backwards, but I'll take it. I had previous experience as from another company building and deploying with infrastructure as code, but it was very bare minimal. So we took on the task and said, sure, we'll do it. The stipulation was that the team, our database admins, would own it, the modules themselves, but DevOps would do all the deployments. So we were just basically blessing the modules and then giving them to DevOps to do what they needed to. Since we are an AWS shop, we wanted to create 2 basic modules, one for MySQL and Aurora MySQL, and one for Aurora Postgres and Postgres RDS. We were already using Ansible for initializing our database. We actually used Ansible automation platform, or Ansible Tower. So we knew we could at least bootstrap that part of it into the pipeline, or at least we hoped. And then it sounded pretty straightforward. And after I had come out of this meeting, I went to my mentor, who was just my manager, and he laughed. And I said, why you're laughing? He said, we did this exact same thing at the previous company, and it basically ended up with them creating a Python script that deployed all the resources. And as somebody who doesn't like to be told it's not going to work, I said, no, let me prove it. So with that said, we'll go into the first stage of denial, or the first stage of grieving, the denial stage. I'm denying the fact that I'm being told I can't do it, and I can certainly do that. So has anybody deployed or looked at any of the providers with Terraform or OpenTofu? Anyone have experience with that? Okay, so, which it shouldn't be a surprise, but some of the bigger providers like AWS, GCP, Azure, most of the documentation that you'll find is great. They've got great examples. You might see some obscure references, but ultimately you've got a clear path on how to deploy the module. However, Ansible is not as straightforward. As someone who is very familiar with it, it didn't take much time. But if you look at the provider, there's very minimal examples, and it actually requires multiple resource blocks to execute a playbook. We already had a runner created because of Ansible or the AAP. So that was already something that was going to be included in our workflow, and the flow itself wasn't flexible enough for our CI/CD pipeline at first. We explained, okay, this is what we're going to do to the DevOps team, and unfortunately, that is really small, but I wanted to map out that the main core part of the deployment was going to be the MySQL version or Postgres version. We would create a KMS key for the encryption, pretty straightforward. And then for the DNS record, we were going to just create a Route 53 CNAME just because it was a lot easier for the developers to use that for endpoints when they implemented that. Then we would have a new module for Ansible Playbook, and then we had a secrets manager tool that had a provider that we would use to create the user credential and then pass that into the playbook. So we presented this to our DevOps team, and they seemed very confused. To me, it felt straightforward. We were going to deploy a database, encrypt it, or use an encryption key, create a DNS name, initialize it, and use our already existing secrets manager. What was really disappointing was, as we said, the other modules didn't have, or other providers didn't have great documentation. This was no different for our secrets manager documentation. It actually just provided examples with 0 words. There was 0 descriptions. It was just, here's a resource block, and this is an example. We didn't have any parameters with descriptions of the parameters, and it was really disappointing. This isn't a secrets manager tool within AWS. This is a complete third-party tool, and I'm just not going to throw shade at them, so I'm leaving the name out of it. So lessons learned on the first stage of grieving. AWS providers are polished. Providers, not so much. You're going to get what you get. What works also locally on our CI/CD locally might not translate to CI/CD pipelines. I didn't mention this, but we were already just building, this deployment method from our local machines. We were not using a CI/CD pipeline. We were just working on it locally because we wanted a proof of concept. And that will bite us in the butt later on. So enter the next stage of grieving anger. So there's a quick diagram I wanted to put up, and of course it's really small, so you might not be able to read it. But what it's saying is we wanted to map out the different types of scenarios that we would get from when somebody would request a deployment. So just a quick recap, we have one provider for deploying the database, one provider for initializing the database, and then we have one provider for creating the credentials for the database. But our DevOps team came in after we displayed the proof of concept, and they asked, what about restoring from a snapshot? It's like, we didn't think about that. It's pretty straightforward, but that means there's going to be more user input at this point. And then there was okay, well, if we're restoring from a snapshot, are we restoring from the latest snapshot or from a point in time? And those provide different paths, essentially. For like the latest, it's a data source that will just look at the latest snapshot that was done, but because of how our snapshots were being scheduled, that snapshot would actually be midday, which is not ideal for a lot of situations. So it ended up being a lot more complicated than we needed to do. And it was not in scope. We didn't set standards. We didn't say, hey, we're going to start with our initial deployment with a blank database. We didn't clarify that, so that's on us. So now we have scope creep, which everyone deals with. So lessons learned here, do your due diligence before you agree to scope. Research what others have tried. Define what's in scope and out of scope explicitly. Sounds very, probably similar to what you hear from a PO, but we should have focused on a blank database deployment first. With that mindset, that would have saved us a lot of time and a lot of struggles trying to develop a within Terraform and OpenTofu a better way of handling this is a snapshot restore, this is a point-in-time restore, or just a blank database. Okay, stage 3, bargaining. This is probably my favorite, mainly because we've already created now this KMS key module, Route 53 module, and our database modules, and our secrets module, and our Ansible module. But what we were finding is that, one, the deployment or execution of the Ansible playbooks was very hit or miss, mainly because something that we couldn't control was that our Ansible runner one day decided to have all of the Python dependencies removed from the VM, which did not help because if anybody uses Ansible, those are dependent. So that made it really difficult for us, and that's something we couldn't control. And ultimately, the initialization of the database was proving rather difficult within testing in a CI/CD pipeline because one, we didn't have we had a tech gap or a skill gap in our DevOps team, including our team. And so at the end of the day, we said, you know, why don't we just trigger the playbook after the deployment by hand, which defeated the purpose of being a CI/CD pipeline, but we had to do this in order to get the thing working. And additionally, too, the idea of trying to figure out how we can automate this, this is what the XKCD diagram shows, is the amount of time put into automating something and how much it actually saves you. We were trying to go through that mentality of, is this really worth putting all of the time and effort to automate something when it literally just means we can point and click? So lesson, sometimes companies lack technical expertise to integrate existing workflows into new ones, and you can always compromise on perfection by keeping the pipeline moving, even if that means manual intervention. That's something that I really don't like to do. I'm really very heavily invested in automation as much as possible. So the fact that before we even got a working CI/CD pipeline, had to make a next step of manual execution was unfortunate. Okay, so, oh wow, this is very hard to see. I am so sorry. So I'm actually embarrassed to show you this, but this is what everything looked like. So our model was, we had a locals TF file for all the parameters per environment. We had your typical main TF for the deployments executing for the modules and what have you. And as you can see, the far left, if you can see, is the local variables. There's lots of them, which means a lot of input and kind of defeats the whole purpose, as well as the large amount of modules that we have to call on just to deploy a database. I presented this to my manager or mentor, and he said, this is great, but he was lying. It's too much. And I looked at it and said, you're probably right. But something that I realized was that I had created something that only I understood, and I like the ability to have the ability to change parameters whenever I want and have that option. And here, this was actually the worst thing I could have done for a CI/CD pipeline. So I'm embarrassed to show you this, but I promise that's not what it ended up looking like at the end. So enter the stage of depression. I had realized I became the gatekeeper, and I'd over-engineered something. What my locals TF looked like a Costco grocery list. Yeah, you go in and you're thinking, I only need 1 or 2 things, and it ends up being, a foot or 2 feet long. This was exactly what happened. And we actually had variables for variables and overrides for those variables because of how our infrastructure was created. Not our fault, right? So what we ended up doing, with the feedback we got from my mentor, my manager, and by just simply bringing in the team to be more involved with this, I'm on a team, or was on a team of 4 DBAs at the time, and was really the only one pushing this method, or pushing this effort. So I ended up creating some one-on-ones with the other teammates, and we had regular check-ins to make sure we were all aligned. But that meant we had to rebuild every single module, which was a good thing, to be fair. We focused very specifically on variables based off of DB engines, and that'll be explained a little later. And we agreed on what we should have done in the first place, defaults for all of the configurations, whether it was Aurora, MySQL, or Aurora Postgres. So after those several one-on-one feedback sessions, we started to see the light, and it started to look pretty good. So lessons here. Know your customers. In this case, it was know my fellow teammates. Parameterization is good, but setting defaults to your team standard configuration is best. Having strong defaults for version, instant class, security groups make modules much easier to use, which I think is pretty straightforward, and I should have realized this, but as lessons are, I learned them. Okay, my favorite step, because there's ice cream. Stage 5, acceptance. So we went from 5 modules to 3, KMS key, Route 53, an Aurora non-Aurora module, and I went down to 7 inputs. So I think there was about 34 before, and now we're down to 7. And there was a lot of internal logic in the modules to do things based off the default engine. So we defaulted to Postgres. If it was a new Postgres, it was usually 15 or 16. And then with that came an instance class that was default, a parameter group that was default, and things like that. We had one subnet group. We had one security group, because why repeat a security group for every deployment when it's literally going to be the same port, 5432 or 3306. We had a manual playbook execution, not great, but it worked and it was working before, so why have to try and figure out another way? And that meant that I could eat ice cream. I celebrate anything usually by eating ice cream. I'm an ice cream snob, and that is my favorite flavor by Tillamook. So if you haven't had it, it's really, really good. Okay, so now this is what it ended up being. I'm really sorry, it's really hard to see. But on the far left is the was the locals TF. So you can see there's only a few inputs. It actually looks a little longer than it should, only because there's inputs for tags, and I don't count that because tags are important. And then in the middle is the main TF. So we got down to just 3 modules and then our outputs, which were pretty straightforward. A lot better, and I was really happy with it, and it was actually really doing well. We deployed about 50 plus databases, which isn't a lot, but they were successful, and it was pretty easy to do for all of my teammates. So lessons learned. Databases are the backbone of IT. Implementing them in infrastructure as code could be much harder than infrastructure. Technical expertise gaps, industry turnover, and organizational changes will impact but it's achievable. And something that I learned in the decade of being in IT is all gray. There's no black and white. It's never one way or the other. It's always in between. So let's talk about what happened. We experienced change in our organization. We deployed 50 databases, and we didn't even manage state file. We didn't manage any states because we basically just deployed it and then managed the entire instances with Ansible. And it made it a lot easier for us, so it defeated the purpose of having a CI/CD pipeline, but my boss was right. And so we never fully implemented what we were supposed to, and at the end of the day, I ended up rewriting the entire thing in Python. So basically, about 8 months of doing this back and forth, the end result was the exact same result that my manager had, and yeah, he was laughing pretty hard at the end of that. So key takeaways: research first. Scope carefully. Something I think everybody hears, and we always laugh at, oh, we couldn't possibly have scope creep, but it always happens. Providers are always they vary widely. I think only found a few smaller providers for things like DigitalOcean or Linode, now Akamai, that are pretty good, but most of the time the big 3 are going to be Azure, AWS, and GCP, which are really good. So 2 or 4, I guess. Know your audience. So build for what your team's expertise are actually that are actually within your team. That's something that was a hard lesson learned for me because database admins nowadays it varies and it has changed quite a lot. We've become more of database reliability engineers rather than the traditional let's go through queries, optimize queries. We're just doing all that and some. So just adding on to it. And that creates a lot of skill gaps depending on the experience of your team. Defaults matter. It's something that I really can't emphasize more, that if you've got defaults for your variables, there's a reason why they always stress it, because then you don't have to provide any input if you're just asking for what is expected. It's okay to compromise. Manual steps are not failure. In this case, they kind of were, but the CI/CD pipeline still lived on outside of databases, and we were still able to provide an easy and efficient way of deploying a database when requested. And context changes. Org changes, priority shift, and roadblocks appear. You just got to go with the punches. And that's actually it. So I was really happy to go through my struggles. I know it is at the end of the day, so I really appreciate you guys all being here. I'm hoping the rest of SCaLE for tomorrow goes well, and I am happy to take any questions or comments or suggestions for future. So thank you. No questions? Yes. They're recording it, but I could hear you just fine.
Hi. So you said ultimately you moved from Ansible over to Python. What's the current state of your Python? What does that look like?
Yeah, so we
just at a high level.
Yeah, we moved from using Terraform and infrastructure as code to using Python to deploy. Currently, that's a good question. I'm not on that team anymore, but from what I've been told, it's been doing great. What's nice about it is for the configuration and standards, it's in a YAML file that they can just take a pull request and change things. But yeah, it's working, it's running, and they're executing it locally just fine. The DevOps team has moved on to other things for infrastructure as code. Good question.
Just so I'm clear, like you just mean like you wrote a script that's like Bodo stuff?
Yeah.
Okay.
It's essentially just the API calls, and the Bodo 3 documentation is really good. It's very verbose, but yeah, it's just calling specific API calls to deploy, and with the inputs that you give it, which are basically just defaults.
Would you be able to comment on what your DevOps team is moved on to?
My opinions are my own. They're not my employers. But from what I know, they're still using OpenTofu Terraform. They just have moved to not using ours or using the database teams. So last time I checked, they were still working with their infrastructure team, trying to implement that pipeline, and that was about 2 years ago. So I don't know.
So I'm curious, you mentioned database initialization. In your experience, because I recognize it varies, how far do you take that? Is it like table creation, index creation,
Good question.
all of that fun stuff?
Yeah, so obviously each company is going to vary on what they need. Since it's a medical, or I work for a company that's in the medical industry, the things that we had to focus on were simply just creating certain restrictions on for Postgres specifically, schemas that can only be accessed by certain users. There wasn't any table creation. We did create a DBA schema to like hold metrics that we would eventually collect. But at the end of the script, it was just generating service users for the app that it was supporting or service, and then the local DBA accounts. We had 4 DBAs officially, so it would just generate users for us automatically. So once we got that endpoint from the deployment, we could just log in and it should be set.
I guess the exception would be the point-in-time recovery kind of scenario where suddenly
it would be a
everything's
restore.
there.
Yeah, we wouldn't even touch an Ansible playbook at that point. But yeah, that would have been more manual, click ops to get that done. We used AWS backup with a capital B, and how that's handled is a lot different than AWS backup with a lowercase b, which is just the built-in AWS backups that you can set up when you deploy an instance. And so it needed more manual intervention for doing the restores. I'm trying not to go into the weeds on that one. It's an interesting thing. You should check out AWS backup. Yep. Any more questions?
Say, we have some time if you want to go into weeds.
Okay, so AWS backup. I guess this isn't really relevant, but I'll talk about it anyways. AWS backup with a capital B is used for being able to back up not just databases. It can do S3 buckets, EC2 instances. It's really meant for sysadmins or IT infrastructure folks to make sure that they're covering all their, dotting all their I's and checking off all the checkboxes to make sure that we've got some sort of restore or disaster recovery for all the deployments or all the resources. How it works is it's not like the actual scheduling you can do for an RDS backup with a lowercase b. You give it a time zone or time window that you can back up, and it uses an algorithm to calculate if it can actually do it within that time or that schedule, and if it can't, it'll pick one for you. And that means that we were getting snapshots in the middle of the day because of how many databases we had, it wouldn't be able to finish that within that time window. But good question.
Other questions? No? Once, twice?
All right.
All right. Well, thank you very much.
Thank you, guys.